So, good morning and welcome back to the live stream or the recorded video, depending on what you view, for the lecture Computer Graphics. Today's topic will be acceleration structures. And those acceleration structures are, well, supposed to speed up the rendering process. We'll look into the acceleration structures focusing a little bit on ray tracing because that's the only rendering approach that I explained so far. But most of those concepts are also applicable for other rendering approaches, such as rasterization, that we will learn later. So keep that in mind, that it's not that some of the things are specific to ray tracing, but not all. So it's not just a ray tracing thing here. But again, I said we've done ray tracing last time, so I want to focus on that one a little bit, and I want to approach the idea of acceleration from a ray tracing point of view. So that's it. This is what we've got so far. So this is our ray tracing pseudocode. I'm not sure if some of you looked into an actual implementation or went through the process of implementing a small ray tracer, which I said is really very easy to do compared to other rendering systems, because it's really only that piece of code here, just basically what it requires you to do is to transfer this pseudocode to whatever the programming language of your choice, and then fill in a few of those calls. A particularly important call is compute ray object intersection, or more specifically, compute the first ray object intersection. And inside that call, we have this loop here, right? So that basically traverses all objects, figures out whether the ray intersects that specific object that we're currently looking at, which is denoted by ID here, and then we'll check if that intersection distance to this specific object, whether that is smaller than the intersection distance that we found so far. So we need to properly initialize that, of course. And if that's the case, we'll store that. And after we went through all the objects, we found the minimum intersection point, the closest intersection point, and we'll work with that. Okay? So as you can see, this will probably take a while, right? For two reasons. First of all, we have to repeat that function itself for every ray. You see that it's called here. Let me just go back one slide, right? So it says here for each pixel. So we have one outer loop that does this whole computation, this traverse computation per pixel or per ray, which is kind of the same if we just shoot one primary ray. And then inside that, we've got this other loop here. And if you have two nested loops, it'll probably take a while depending on how big these loops are. So there's hopefully some opportunity to accelerate the thing. Before I want to do this, however, I'd just like to quickly repeat something from your bachelor's classes. And this is also why the color changes here, because I literally copied the bright slides from second semester computer science, data structures and algorithms class. So I just want to quickly repeat a few things, namely what I talked about in theory of algorithms, and just to kind of get you all onto the same level. So if we analyze a problem, or if we analyze an algorithm, which is actually not exactly the same thing, most people think that it's the same, but it's not. An algorithm is just one particular solution to a problem, but there might be more efficient ones or worse ones. But first of all, there's one type of classification that we can do. We can figure out here, what's the best case that can happen? What's the worst case and what's the average case? Okay, to give you a simple example, if you do a binary search for an object, so meaning or let's just do a linear search to make this even more simple, right? You have a sequence of elements and you just want to find one element, whether it exists, and if it does, where it exists. Then your best case solution is you start at the beginning and you run through this, and your best case solution is the first element that you touch is the one that you're looking for right away. So you're done immediately. Your worst case solution is you have to scan this thing to the end and you either find nothing because it's simply not there, or the very last element is the one you're looking for. So this is your worst case. And then there's the average case, which is, well, it's somewhere in the middle, and if you don't have any clue where it is, the average would be that it's on average in the center, right? So sometimes more in the front, sometimes more in the back, but on average you have to kind of scan half the list. So this is this is this idea of average, worst, and best case. In general, in data structures and algorithms, I said we'll focus on the average case because this is really the one that you're most interested in. Best case, really, I'm not aware of any really crucial situation where the best case is a big deal. Why? Because, well, unless the best case happens to be equal to any of the other, it's just nice to know that there's opportunities for early out, but since they, in particular, if it's different from the average case, that means it doesn't happen regularly, then you don't care much about it. So it's only an academic thing. However, the worst case was something that we didn't look much into in data structures and algorithms, a little bit, for instance, when we looked at quicksort in comparison to other sorting approaches. But in general, we were interested in the average case. In computer graphics, however, a worst case analysis is also important. Why? Because when you do something that you need to do per frame, you do during your rendering process, and you have a worst case complexity that's significantly, well, worse than the average case, then this might mean that some of your frames may be incredibly slow as compared to others. And this is something that shows, right? This creates choppy animations or whatever. So in computer graphics, it's actually a situation because we're dealing with real-time systems. And every time you're dealing with real-time system, you're also interested in the worst case. Okay, but that's obviously one way to classify algorithms, and I don't want to go into the same details than I do in data structures algorithms. Just supposed to be a quick refresher here, but there's another way how we think about complexities in general, and that is we can think about a complexity of a problem. So you're given a problem, say you have to sort something, you have to render a scene. You have to find an object, where sorting and finding an object happens to be parts of render a scene. So those are actual problems. And then you can try to establish a difficulty for that problem, right? So is it possible to, or is it not possible to solve this problem any faster than whatever, right? So this is one side. And then the other side is you look at specific solutions to a problem, right? So if you think about sorting, you look at bubble sort, or you look at quick sort, you look at selection sort, or whatever. And you look at the time it takes to do that. Oh, thank you. The time it takes to do that, the complexity it takes to do that. Okay, so and those are two things, again, that you need to distinguish and that students often mix up. The difficulty of a problem or the complexity of a given approach. Okay, and this is just basically what I want to stress here. And this relates to concepts such as upper bound, lower bounds, and then ultimately, if the two agree, optimal algorithms. Okay, so an upper bound is usually established. You can do this by theoretical means, but it's usually established by presenting an actual implementation or presenting an actual algorithm. So if you're given a problem, say sorting, you're supposed to sort a list. And you present an approach, say, I don't know, bubble sort, to choose something dumb. You can say, well, bubble sort takes n squared in time, and n given being the length of the sorted list. Then the sorting problem cannot be harder than n squared because I've just shown that I can solve it. Okay, so this is an upper bound. So an upper bound is often a given complexity of a given approach. So a lower bound is usually not presented by the means of an actual implementation, but by a theoretical consideration. To also give you an example, find an element in an unsorted list. So you're given a list that has no structure to it, whatever, and you want to figure out if a given element is in there. You have to look through, at least with traditional computers, you have to scan this list from the beginning to the end. Why? If I just skip one element and I have no clue about the distribution of the elements, this one element might be the one that I'm looking for. So I need to look at every element to be certain that it's there or it's not there. Okay, so with that consideration, I can easily argue that at least it takes linear time to look at all, to figure out whether an element is in there or not. So this is a lower bound. And then if I present an approach, for instance, to solve the problem within that lower bound, then I have found an optimum algorithm. That in turn means that, because it says here within a constant factor, which is what you usually ignore, that there are multiple optimum algorithms, and that one optimum algorithm might be faster than another optimal algorithm, okay? Because one might just be 100 times faster, right? Because 100 is just a constant factor. So this is a little bit, well, it might be a little bit awkward to define it this way, that optimum doesn't necessarily mean it's the fastest possible, but that's how it's defined. And this results in basically three types of functional descriptions, so to say. So there's big theta, big O, and big omega. And this is kind of the slide I really wanted to get to, because this is what, in particular, the big O notation is something that I'm going to use in this lecture from time to time. And I just wanted to basically refresh that you know what this is. So this big O notation is to develop the upper bounds. So this big O notation is a notation that says, okay, depending on some input criteria. So for instance, the length of a list, the number of pixels, the number of objects in the scene, whatever, something that depends on the input, that describes the input, that describes the length or complexity of the input. Depending on that criterion that I just call n here, again, n could be number of pixels. Depending on that one, how long does my given implementation take to solve a problem? Okay, sorting or render the scene. Okay, that said, since it's a given implementation, it is an upper bound. Okay, if it solves the problem, if it solves it in, say, n squared, I know that the problem of rendering itself has an upper bound. So this is this kind of duality that on one hand, this O describes a particular approach, but it also describes the problem at hand. For the particular approach, it describes just how that approach behaves. For the problem, it's an upper bound. Okay, and just, I'm not going to use those much here, but just so that you know them. So there's also big theta, and then there's big omega, and those are the two others. So this is basically big omega is the lower bound concept, and then big theta is the classification of an approach. So this is the actual complexity of a problem. Okay, so this is big theta, then is in between those two here. Okay, so just to give you an idea what these things really mean, because a lot of people actually have this misconception that the O notation is like if you have a problem of O of n. That's not necessarily wrong to say you have a problem of O of n, but that doesn't mean that this problem takes linear time. It just means I have one solution that takes linear time, but it might actually be better. Right? Technically, if you talk about problems, you usually want to talk. You would want to talk about thetas. But that's, again, just a refresher here. So finally, just one example, and then I'll return back to computer graphics. So just a super simple example. One sum. We'll also talk in data structure about two sum, three sum, and so on and so forth. So basically, those are the hard problems. But one sum is a very simple problem, and that's just, is there a zero in an array? Okay, two sum is, just to give you kind of a outlook here, two sum is there any pair, or are there pairs in our array that if we sum them up equal to 0? And then three sum is, are there triplets that sum up to 0? And that's a really important problem, by the way, in particular in computer graphics, in geometry. That's a very important problem. But anyways, one sum is kind of the trivial version of that one. Is there a 0 in an array? Okay, and just to kind of go through this, we can develop an upper bound. So we're simply implementing a brute force approach, right? Brute force means you'll just use a very simple idea, and you're willing to spend a lot of time solving the problem, okay? So the simple idea is just look at every element, okay? And obviously that takes linear time, right? So if we have to look at every element, then obviously the length of the array is our complexity means here. Then we have, we spend linear time, and that means we have now O of n runtime for an approach, and we have an upper bound for the problem. Now, again, the lower bound here, same consideration as before with the searching. if you want to figure out if there's a zero in the array or how many zeros are there, you can kind of both are sort of the same problem. I have to look at every element, because the one element that I skip, or the two elements that I skip, might contain a zero, and since when I've looked at the others, I can't rule out that those are zeros. So the lower bound is obviously also n, so I've got a big omega of n, and if the two agree, the lower and upper bound, then I know that theta of n is also linear. Okay, good. Any questions about that concept? So as I said, that's really second semester bachelor's level stuff, but nonetheless, are there any questions about that? Okay. Doesn't seem to be the case. Good. Then let's apply that to our rendering problem, in particular to ray tracing. So in ray tracing, since we have these two nested loops that I presented at the beginning, one loop over all pixels and one loop over all objects in the scene, we can develop a upper bound complexity for the problem of rendering a scene or ray tracing in general, and then looking at our specific implementation, and you can say, well, this is O of m times P. Okay, why? Because, well, m being the number of objects and P being the number of pixels, it'll take O of m times P time, because I need to look at every pixel, and in every pixel we need to look at every object. So that makes O of m times P. Notice that I haven't mentioned that here. In the O notation, we skip any constants. So whether that's 100 O of m times P, because it takes 100 operations to compute that intersection, or 1,000,000 or 1,000,000,000 or 5, doesn't matter. So any constants that we multiply with m and p are dropped. Okay, and also any lower order terms. So if it's m times p plus p, we would drop the plus p as well. Okay, now okay, that I guess makes sense. So now, why is that bad? Well, if we have polygonal objects in the scene, which we often have, right? We often break down our objects into polygons, and usually those polygons end up being triangles. And then we can replace the m, we can replace the objects by the number of triangles. Because what does it take to intersect one triangulated object or one polygonalized object with the ray? Well, we have to look at every facet, every triangle, every polygon separately. Okay, so it ends up being O of n times p, whereas now n is the number of triangles, and that's usually considerably higher than m, right? Every object is usually made up of potentially millions of triangles, and that can be pretty big. It's still linear, okay? So from a pure theoretical point of view, you could argue, well, linear scales. Linear does scale pretty well. Lower order complexity scale better, but in most scenarios, you're actually pretty happy with linear complexity. And well, yes, in a sense we are. So I mean, it's not that slow that it takes years or decades or whatever to solve. But remember, it's a high performance problem, and it's a real-time problem. So we need to generate a ton of frames per second for things to be interactive. Okay. So the fact that we really have to do this, all of these checks, every intersection with every polygon, every object, every frame, every pixel is it happens to be a big deal. Okay, so we need to make that quicker for this to be more more interactive, or even if it's not interactive, then at least faster, so that it doesn't take hours but only minutes to generate frames. And it's surprising where you need performance, right? Just to give you one pointer here, if you do production level graphics for a movie, say you want to render a Pixar movie or whatever, an ILM movie where you have special effects in there. Of course, those movies aren't rendered in real time, but they're rendered offline and then they're composited. But it makes a difference when you, as a director, set up a new scene, whether it takes a week or a day or an hour or 5 minutes to get some result back. Okay, so here time is also money, and that's something you should not underestimate, how long it takes to render render movie sequences. So even in high quality production level graphics, time is actually a big concern, surprisingly. Okay, now how can we speed things up? And there's three things in particular, considering ray tracing for a second again, that we can do. We can speed up the ray object intersection. I mean, this is the most inner core, right? So we have, for every pixel, for every object, compute an intersection, right? So the innermost computation obviously gets executed very often, so we should speed that up. So maybe we can find a more efficient intersection. Notice that this is something that I haven't considered in the that I haven't considered in the O notation, because it's just a constant, right? So we have number of pixels times number of intersections, and then times whatever an intersection costs. But since that is usually a constant, it doesn't show up in the O notation. But this is very important here. But it makes a difference if you render your game with 100 hertz or 1 hertz, right? So this constant of a 100 suddenly makes a huge difference. So it makes sense to work on that constant. So the other thing is, we can try to reduce the ray object intersection. So maybe we don't need to look at every object with every ray. So maybe like if we found an intersection and we cleverly do this, right? So for instance, we start from the front and then progress towards the back. If we found an intersection in the front, then we don't need to look at the back anymore, right? So that might be an idea. Now the question is, what's the front? I mean, that changes, right? The scene is potentially dynamic. The viewing direction is dynamic. So how do we how do we do this? More on that later. And then finally, fewer arrays. Is there a possibility of maybe not shooting an array for every fragment? Sorry, for every pixel on screen. And I'm not going to go over the last one, so that this I want to skip here, but I want to look at the first two. So the last one is a rather complex idea here. In particular, when you say you only shoot every second ray, you obviously have your frequency, your sampling frequency, so that creates aliasing. You need to counter that aliasing, and there are very recent approaches to address that, using in particular machine learned filters, so very sophisticated filters. But for now, this is beyond the scope of computer graphics. So we'll probably address that in advanced image synthesis next semester. So let's look at then look at the first two things, and let's just start with faster ray object intersection. And for that, let's again do a repetition. So you'll notice that today, in today's stream, I'll have a lot of these repetition things here at the top. So we had the repetition from data structures and algorithms, and I'll also repeat a couple of things from this very stream here. So this won't be the last, and this is just to kind of, and I'll not continue to do this through the rest of the stream in the coming weeks, but I want to do this once to just give you this reminder that I'm now at a point where I'll start to use all those little puzzle pieces or Lego bricks or whatever you want to call them, and I want to build things with those bricks, okay? So back to geometric models 2, I talked about linear interpolation, okay? So I talked about this idea, how do we figure out the interior of a given, in this case again, a triangle, okay? So I'm given properties, for instance colors here, at the 3 vertices of the triangle, and I want to know, okay, I don't want to just draw the vertices, I want to draw the interior, I want to draw a completely filled triangle. How should I fill it? What color should I assign to what color should I assign to that point, this point, or that point, for instance, right? And for that purpose, which is by the way called shading, this filling out things, I need to develop a method called interpolation. That is, I need to take other values into account and figure out the in-between, okay? And an interpolation has a particular, an interpolation function has a particular quantity, namely that it returns the original values at the vertices. It should not change those, but it can return anything in between. And you can develop a ton of different interpolation functions. And what we wanted to look at in geometric models 2, and what we want to use here, is linear or barycentric interpolation. So this is basically the same thing. And the idea is that we want to find a linear function that, well, fills the interior. And the way we approached this when we did barycentric interpolation was we basically said, okay, we want the simple formula. We just take the quantities at the 3 vertices, and that could be color, it could be position, a normal, whatever. I just take these quantities. Let's say we do this with color, so to just make things simple here. So this is the color of the first vertex, second vertex, third vertex, and for any point x, so x is now a vector, so any point x inside the triangle, I want to compute its color f here simply as a sum of all the other colors, whereas those get multiplied by weights, and the weights should just sum up to 1 and should all be positive. That means they're between 0 and 1. Okay, so we also call this a convex combination of the values or barycentric interpolation. And just as a side note, we can also do this for the very coordinate of x, right? So if we throw in x into this function and as f's, we use the positions, we actually, it would be nice if we get the position out of x. So in particular for barycentric interpolation, that is the case. And how does barycentric interpolation work? How do we compute these 3 parameters that we use to weight the 3 values at the vertices? And there's one relatively simple way, which is based on the areas of triangles, which I got here. So if we're looking for u, which is the weight for the point 0, we simply compute 2 areas. So one area is the area of the triangle itself, okay, which I call A. Okay. And the other area is the area of a subtriangle here. And that is a triangle that is constructed out of the 2 other vertices, the one that are not the one that I'm currently, whose value I'm currently computing. So I take the other 2 vertices and I use the vertex in question. The one that I'm interested in, the one in the center here. So that also makes up a triangle. It might actually just become a line if I pull this down here, or technically it might just even be worse if I move this to a vertex itself. But let's just look at the normal situation, that it's somewhere inside the triangle. Then I get a second area here. Okay, and now if I divide that smaller area by the larger area, first of all, as long as this point stays inside the triangle, this u satisfies the condition that is between 0 and 1, right? If I pull this onto any point on this line here, u becomes 0, so the area of a0 then is 0, 0 divided by whatever is 0. If I move this point x here towards this point x0, then a and a0 at one point will become equal, so at that point this becomes 1, and it cannot be bigger unless I move the point outside, which gives you kind of a pointer to how to detect whether a point is inside a triangle or not. You can tell this by simply computing this value here and then check whether it's negative or bigger than 1. Okay, with that I can compute values that are between 0 and 1, and if I repeat the process with 1 and 2, x1 and x2, you can see that obviously u, v, and w sum up to 1 because these 3 subtriangles make up the triangle A. So they will sum up to 1. And with that we can use them. We can use them in this computation here. So for instance, to compute the point, or for any other quantity, to figure out where are we inside for the position, or to figure out what should the color be at that point. Okay, so what are we going to use that for? Stay with me for a second. I'm just collecting building blocks. So here's another building blocks that I just quickly want to repeat. And that is, how did we do a straightforward object intersection? We wanted to make intersection faster, right? So that was kind of the point. How did we do it slow? How did we do it before? And again, I just want to focus on simple situation, triangle to ray intersection. Okay, so here's what we just had. Here's any point inside the triangle satisfies this condition. I said we can do this interpolation not just for colors or anything, we can also do it for the position itself. Okay, so that means any point P inside the triangle, if the triangle is made up of the points P0, P1, and P3, can be written as U times the first position, V times the second, and W times the third. And we have this side condition that U plus V plus W always sum up to 1, and neither of them is smaller than 0 or bigger than 1. That means I can eliminate one parameter. For instance, I can eliminate U. I just replace it by 1 minus the other two. Okay, because they sum up to 1, well, then obviously 1 is superfluous. I can just replace it here. Okay, let's do that. And then let's just rephrase this, or let's shuffle the terms a little bit. So we'll just sort them by the now V and W. Okay, so here we also have them sorted, but here we suddenly got the V and W mixed up. So I'll basically just multiply the first term out and then sort it by V and W so that I get this here. So I now have a constant part, P0, and then I have something that depends on V and something that depends on W. And then also you can see, well, this is, by the way, our linear function. Okay, so this is the most simple linear function. A plus VB plus WC is the most simple linear function that you can come up, or it's a general linear function in 2D. Okay, well, now we've got that, and then we wanted to compute the intersection with array. And again, this is literally slides that I copied from Geometric Models 2. So I didn't change them except adding that red description at the top. So if all that sounds familiar, good. If it doesn't sound familiar, well, you either skip the stream or you've completely forgotten that I talked about this. Okay, so now let's compute an intersection with array. So that's what we're interested in. So here's my array, and here's again here's the general description of array. So what's array? Well, it's a thing that starts at some point. Let's call this PS for starting point, and then it progresses in one direction, which I call D here. Okay, so then any point on the array is P plus D times some quantity. Okay, so for instance, a point that's 1 unit away is P plus T plus 1 times D. A point that's 2 units away, it's P plus 2 times D, and so on and so forth. So I can just generate points with that equation. Now, if we want to figure out where does that ray intersect that triangle, so where do the two agree? Where do they have the same value? Well, if I want to know where do they have the same value, I just set them the same. Okay, so just say, like, literally, I mean, this is actually very funny. It's like, where do they, this one have the same value? Well, I can't find the point, the pinpoint value, but same value is really equal, right? And then we simply solve that, right? And this is pretty much where I stopped at Geometric Models 2. I said, well, this here, well, I think I went 1 or 2 slides further, but the basic idea was, like, what have I got here? Okay, what are the unknowns? Well, the unknowns are all the lowercase characters. I've written them lowercase here. W, V, and T are the unknowns. PS is known, that's the starting point of the array. D is the direction of the array. P1, P0, and P2 are the 3 coordinates of the 3 vertices of the triangle. So those are all knowns. So we end up with 3 unknowns. And we have a system of 3 equations. This is just one equation. Where do the other 2 equations come from? Well, this is in 3D, right? So we have this equation for x, for y, and for z. 3 equations, 3 unknowns, gives us a thing to solve, right? And we can either solve this by the means of just linear algebra, inverting a matrix, or you can do, which is technically also linear algebra, you can do any other technique to solve just all 3 equations with 3 unknowns, right? So this is really school stuff. Okay, and that's where I stopped, right? I said we can do this, okay? And basically now, if we want to speed this up, I want to talk about how to do this fast, right? And I only know very few things in computer graphics where so much energy has been spent in optimization. And this is one of those areas where a lot of papers, a lot of approaches have been developed to make this faster and faster and faster. And I just want to talk about a fairly old technique, right? We're talking about something that's apparently 23 years old here. So why do I pick such an old approach over any newer research? And as I said, there's a ton of research going into this. How can we make a triangle array intersection test fast? The reason is very simple. that pretty much all the research that came after this paper by Thomas Möller were derivatives of the theme of the same idea, just tailored to very specific hardware. So literally you find in the literature the optimum intersection approach for the Pentium 4 revision 3. And then there's an optimum intersection approach for Pentium 4 revision 4, if that even exists, I don't know. But you get the point, right? So basically what people started to develop were approaches that are very, very specific to a very specific architecture, right? And even to sub-architectures, right? So what happens if your P4 is that model and has, I don't know, 10 kilobytes of cache, or 12 kilobytes of cache, or 12.5 kilobytes of cache? You might want to tweak your approach slightly. Obviously this is only useful for a certain period in time. So this is why I just want to talk about the very basic thing. And these approaches again are very specific to the architecture, meaning that there's a lot of awkward things that you tend to do. So sometimes you do more computations, but you do a few less memory reads, which is beneficial if your cache is small or whatever. Okay, so that as a motivation why we'll use that one. I can give you a pointer though to a nice repository where people collect these intersection tests over time and classify them and say, okay, well, this is not for that architecture and this one. And that is a final note about this one. If you're looking at a high performance ray tracing these days, then they actually they either focus on a specific piece of hardware. So say, okay, well, it's a high performance ray tracer, but you have to buy the newest Intel whatever chip. Now, guess who developed those piece of software, like Intel, for example, right? There's a system called Embry that is specifically tailored to modern Intel chips. It's a very fast ray tracing system, but happens to be that you have to buy their latest and greatest hardware to make it work fast. Or if you have a more general system that is maybe not created by someone who's interested in you buying their newest hardware, then it ends up having a ton of these intersection tests, and then when the system starts, it just analyzes your system. Okay, what CPU do I have? How many memory do I have? How much cache do I have? And then it chooses one specific implementation. Okay. Now back to this approach here, which is kind of the mother of all other approaches, or most, and the other reason I like it is because it uses a concept from math that is usually totally useless unless you do theoretical consideration, and it makes practical use of that, which is the Kramers rule. And that I always found very intriguing, that I finally found beyond theoretical proofs or consideration an actual practical implementation for Kramers rule, which is something that you learn at school, that you learn in your basic linear algebra class, and you generally just use it to prove things. And usually your professor gives you the side note of, oh, well, don't use this in practice because it's that slow, to solve linear systems. Okay, now let's just get my head out of the way for a second here so that I can actually read that. So what does this fast triangle intersection test do? Well, it computes an intersection of a ray with the triangle, among other things. So obviously, as the title implies, it computes a triangle-triangle intersection test, but part of this triangle-triangle intersection test is a triangle array intersection test, and we'll focus on that one, okay? So, but if you look at the paper, or you look at my late-night coding streams, you'll see that a triangle-triangle intersection test generally contains a triangle array intersection. So, what we want to do is, we've got an intersection at some point with a ray, and it's the origin plus a direction times the parameter t, and you want to figure out the intersection point in barycentric coordinates. You want to find the u, v, and, well, you get the w for free. So you only need to find two of those three. So, again, here's pretty much the formulation from before. I just adopted the letters from the paper. I figured that's kind of fun to kind of stick with the actual letters of the paper. So the only difference from what we did before was basically that I called the origin of the ray PS, and and that's pretty much it. I think I've done the previous computation using the parameters u and v and w, and here it's u and v, but I mean those are just variables. Other than that, it's the same. And now we can just resort things a little bit different than we did before. So what I do here is I'll basically not resort things by first looking at how can we get things to be P1, P2, and P0, but here I want to separate variables from constants. Okay, so notice that here I've pulled the constant on one side, the isolated constant, right? O is not multiplied with anything. P0, if I multiply the first term out, I got this P0 times 1. So this is also not multiplied with anything. So I pull those to the right hand side and pull all the variables to the left. Okay, and now I can here also sort the variables if I want to, right? So for instance, the only thing I have to do is I have to kind of combine the two things that depend on P0, which is U times P0 and V times P0. Right? So the others are already pretty much separated. Okay, so we do if I do this, excuse me. So, or I can also sort it by the unknowns. If I do this, then you see that there's something that gets multiplied with V, which is P2 minus P0. There's something that gets multiplied with U, which is P1 minus P0. And there's something that gets multiplied with T, which is minus D. Okay. And now a thing that I'll end up doing very often in computer science in general, in particular in computer graphics, is I'll rewrite things in a matrix vector notation. Okay, so why? Because that significantly shortens equations. We'll do this in AI very often, and we do this in computer graphics here. So I can simply express the term in the second row by just having a vector matrix product. Okay, the vector is simply T, U, and V. Those are scalars. To just kind of write this flat, I've said, okay, T, U, and V transpose is then T, U, and V straight, right? So this would be a T, U, V vector multiplied with this matrix. Okay, what's the matrix? Well, the matrix is made up of 3 vectors. D is a vector, right? D is a direction vector. P1 minus P2 is also a vector, and P2 minus P0 is also a vector. Okay, so those are 3 column vectors. Then if I put them one after the other, we get a matrix. Then if I multiply this matrix with this TUV vector, then I get, well, I get a vector, and that happens to be the thing at the top, or at the second row. Why is that a vector? Remember that is P, those are all vectors, P1, P2, P0, so you always have an X, Y, Z version of the same thing. Okay, so why is that useful? Why does that make sense? I mean, I said I often do this to shorten things. It doesn't really look much shorter. So if I look at my slide, it looks like it's actually a little bit longer because there are now brackets around things. So, but now let's apply Cramer's rule, and then we'll see where that makes sense. So again, Cramer's rule, in case you don't remember, that's a way to solve a system of equations by the means of determinants. And it's a pretty strange thing. I'm not going to prove Cramer's rule here. It's actually not hard to prove, and you should have done this in linear algebra. But I just give you the final result. And the final result is that you, to solve a system of equations, you basically take the matrix and you replace one column after the other by specific unit vectors, and then compute the determinant of that matrix, and in the end you divide the determinant by the determinant of the matrix itself. Okay, so and I've just shortened this thing here a little bit. One thing that I forgot to mention is you replace one one column with the solution vector. So the solution vector is O minus P0. Okay, so I simply call this T here. So I first replace the first column by T, then the second one, and then the third. Okay, and the columns, just to make things a little bit shorter, I just call them, one is already minus D, so that is already pretty short, but I just basically call this E1, which is the first subtraction, and then E2, which is the second subtraction. Okay, so basically I replace minus D here. So this here is the original matrix, right? Minus D, then this thing here and then this thing here. Okay, so first of all, we replace the first one by this term. Compute the determinant. This is what these lines are supposed to mean. Then replace the second one by the right solution, compute the determinant, and then replace the third one. So I basically compute 3 determinants, and then I compute a fourth one, which is the determinant of the matrix itself, and I divide all these 3 by this determinant, and then I get T, U, and V. Okay, so again, if you can't remember how this works, just look at Wikipedia for Cramer's rule, or look at your math book, or simply remember your course. And this works, but it has a lot of disadvantages. So one is it takes relatively long, it takes a lot of computations to compute these determinants, in particular for bigger matrices, right? If you don't have just a 3 by 3 matrix, but bigger ones, computing the determinant is very inefficient. So any other approach, and be it something as stupid as Gauss elimination, is faster. So this rule is really only used to prove certain things. But, and now comes the big but, there's an interesting twist to this when you throw this at a computer for a 3 by 3 matrix, and when you do this in this particular setup. Okay, let's look at this setup here in a little bit more detail. So it happens that there is a thing called a triple product, which is something that you've probably not heard before. And the triple product is a combination of a cross product and a dot product. So it turns out that if you want to compute the determinant of a 3 by 3 system, which is made up of, well, 3 column vectors, and in this case, let's just focus on this one here. Let's focus on this one here. Minus the E1 and E2, you can compute the determinant by throwing a minus sign at the first vector, then taking the third, the cross product with the third, and taking the dot product with the second. Okay, and again, you can prove that it's not a big deal. You basically just run this through with all variables, and then you compute the determinants with all variables, and you see that in the end you get the same result. And this only works this easy with 3 by 3 matrices. But nonetheless, it works for these. Okay, so basically I can rewrite this here as D, notice the minus is gone here, and notice that the order of these two vectors changed. So it's D cross E2 times, this is a dot product here, times E1. And I can also do the same on the right hand side. So now let's look at these two things here. And what you'll probably notice is that there's some similarities here. So for instance, that this term here shows up twice. Okay, and then this term here also shows up twice. Okay, so why is that the case? Well, because, well, we had a minus D and an E here, so, and those also show up here. And then here we have a T and E1, and well, now we've got the T here and the E1 there. Why is that the case? And for this to work, I use a determinant rule that allows me to swap vectors. Remember, when you were introduced to determinants, you were allowed to swap vectors. You just had to change their sign depending on how many columns you swap them. So if I cleverly swap that, it turns out that these two here are also the same. And this is nice because you only have to compute this once. This is particularly nice because this dot product here is no big deal. That's a multiplication of 3 scalars and an addition. Okay, so dot product is pretty simple. A cross product takes a few more computation. Okay, it's not like this is a million computation, but nonetheless, it's a little bit more work. So in this case, we can save ourselves half of those computation. And then this all combined suddenly makes this concept a lot faster. Okay, I can just basically rename things a little bit here by saying, okay, well, I call this one thing that I reuse often Q and the other one P. Okay, and then once I've computed P and Q, this ends up being just a bunch of dot products. Okay, and again, dot products are easy to compute. Not that they're just easy to compute, but they're also vectorized these days. So both graphics cards as well as CPUs can compute dot products in one go. So there's specific assembly instruction for those. So that's one, and there's an even cooler thing about this. When can this thing go wrong? So first of all, when can a remember we're doing a ray triangle intersection here, right? So just to kind of relate this back, after all this mathematical trickery, relate this back to the problem at hand. We're trying to compute a ray triangle intersection. And well, guess what? A ray might not intersect with a triangle. That can happen. There's two reasons for that to happen. One is the ray happens to be parallel to the triangle. That's one situation. And the other one, it intersects with the plane of the triangle, but it doesn't intersect the triangle. Okay, so now the latter thing you can detect by just looking at the u and v. I said you can figure out whether a point is inside a triangle by just looking at u, v, w and check whether they're all between 0 and 1. So what you do here is technically you first of all compute t, u and v for a ray plane intersection, and then I look at u and v and check whether they're between 0 and 1 to see whether I actually hit the triangle. So this is the second case. But what's with the first case when the ray is parallel to the triangle? This is a very nasty case because it produces singularities. Now the cool thing about this approach here is that I can actually easily detect that singularity by looking at this quotient here. Okay, and when do I have a singularity here? Well, this is when this dot product of p and e becomes 0, because then I divide 1 by 0, and that is not defined, and then I have this situation of a parallel ray. And we can even look at that. You can actually take, this is probably something that we should do in an exercise, like figure out what the meaning of p times e1 is. Okay, so when is p times e1 0? Okay, well, that's when it's parallel, but why is that the case? So it's probably the 20-second thing, but you might want to look at that yourself. So why is that beneficial? Because what we do is we compute p first, compute the dot product with e1. If that's 0, we bail out, we say, okay, well, no intersection. If that is non-zero, we know that there is an intersection with the plane, and we can compute u by simply taking that p that we've already computed and computing another simple dot product with t. So again, it's a very simple computation. It's probably a 1 clock cycle operation on a modern processor. And then we already know u. If u happens to be negative or bigger than 1, we can again bail out. So no need to do another computation. If that happens to be between 0 and 1, we compute, wait a second. What's wrong here? We compute q times d and check whether that thing, which is v, is between 0 and 1. And when we sum it with u, whether the sum of the two is still smaller than 1. Okay? If that's the case, we can either simply return u and v if that is sufficient, or we can also quickly compute t, and generally you compute all three of those quantities and then return them. So bottom line is you have 2 early out possibilities for, or you have 3 in total, right? So you also need to check whether these 2 in sum are bigger than 1. You have 3 early out possibilities that are all pretty easy to compute, and even the entire computation is pretty minimal. So as I said, there are a lot of computation that build on top of that, but they actually do more. They tend to do more computations in an effort to better utilize things such as cache and memory. Okay, to do a few computations more while waiting for memory to arrive from background memory, while waiting for data to arrive from background memory. Okay, but nonetheless, that's a pretty cool thing. And with that, well, you can make the intersection test itself faster. So that significantly speeds up your ray tracer. Or in other words, you would always implement your ray tracer this way, even if you do a very simple implementation. Okay, so that was acceleration 1. The second one is, how do we do fewer ray object intersections? Okay, and I already gave you this idea of, like, can't we do this front to back? Can't we just first check the frontmost object, and then if we find an intersection with that, stop? Okay. Well, the question is, how do we find the frontmost object? Okay. So what this generally requires is sorting. Okay, so we generally need to sort things. Now, what's the complexity of sorting? Right? Data structures and algorithms. We know that at least if we approach sorting with just a comparison-based approach, it generally takes n log n time. Okay, whereas n is the number of objects. Now, ray tracing itself is linear. right? It's linear in the number of pixels, linear in the number of objects. Now, sorting is in log n, which is obviously worse than linear. So to make a long story short, if you first sort things and then render them, you'll have increased your complexity from linear to n log n, which generally is not a good idea. There's a lot of details to this which kind of invalidates this statement to a certain degree. That is, for instance, well, you could argue, well, I don't have to sort every frame, right? If the scene didn't move too much, if I don't move, I probably can reuse the sorting from the previous frame. Yeah, true. At some point, your sorting might be off, so it might be incorrect. Maybe we can tolerate a few inaccuracies. Or other considerations you can do is like, okay, well, there's certain sorting approaches that can work with partially sorted lists, right? We know that if lists have certain conditions that they're partially sorted, and again, data structure algorithm for the definition of what partially means here, then we can sort them in linear time. And there's other itty-gritty details to this, which in summary say, well, sorting isn't such a humongously bad idea. But one thing is true, and that is, you can't really get the sorting below a lot below linear, okay? So you need a set of very, very strong conditions for that to become better than linear. So bottom line is you can't really reduce the overall complexity this way, but you can again potentially gain a constant. And as I've motivated before, constants are good. Constants are your friend in real-time systems. I don't want to go into sorting though, but I want to look at another concept, and those are bounding volumes and spatial partitioning schemes, which are really some concept of sorting. So they're very related to sorting, as we'll see. So let's start with bounding volumes. Okay, so what's a bounding volume? It's a pretty simple idea. So we throw a simple volume around complex objects. So here's our teapot again, and I can throw a circle on the left, or in 3D that would be a sphere, right? I can simply compute a sphere around my teapot, or I can compute a box. And both are actually pretty simple to compute, right? Let's say our our teapot is rigid, meaning that I don't let it explode or anything crazy. Then, well, what does it take to compute a sphere? A sphere is just two parameters, right? Center and radius. What's the center? Well, I just pick the center, I take all the points, compute the average, voila, here's your center. And then I simply compute the distance to the furthest away point from that center, and I got my radius. Done. How fast can I compute this? Linear time. Well, I scan once, find the center, scan a second time, if I want to implement this a really silly way, but we could do this. Okay, scan a second time and then compute the distance to all points, take the maximum, done. Okay, so that's easy to compute. And also for bounding box, at least for axis aligned bounding box, it's a similar process. More details on that in a few minutes. Okay, bottom line is just we can compute them pretty easily. Okay, as long as the objects don't do crazy things, we don't even have to update them. So it's a one-time thing that we can do during load. Now, and here's what we do once we've got this bounding box thing. Let's say this teapot is made up, just for argument's sake, of 1,000 triangles. Now, if I want to render that, again, I have to compute this ray object intersection. What I could do is I could first compute. Let's stick with this thing here, the sphere, for a second. Okay, I can first compute the intersection of the sphere with our ray. Okay, you look up sphere ray intersection. We've talked about that early in the lecture, or you can just look this up in your textbook of mathematical solutions. So, and it turns out a ray sphere intersection can be computed pretty simply, pretty trivially, and also a ray box intersection. It takes a little bit more to do a ray box intersection, in particular if it's not axis aligned, but it's a relatively simple computation, meaning it requires relatively few steps and it can be executed fairly quickly. Now, what happens if I do this first check? Well, two things can happen, right? The ray might hit the sphere, or it might miss the sphere, or technically it can touch it, but let's assume that it's also hit it. Okay, so we got these two situations. If the ray misses the sphere, we'll look great, because then since the sphere encloses the teapot completely, there's no reason to look at those 1,000 triangles, and we can avoid having to do the 1,000 triangle test. And if this object is more complex, say 1,000,000 triangles, we can even save us a million triangle intersection test. Okay, now if the ray hits the sphere, we haven't really gained any knowledge. Why? Because it might still miss the teapot, right? So for instance, if it goes through here, it might still miss the teapot. It might go through here, it might hit the teapot, but we don't know which triangle it hit. So at that point, well, we have to go through the same trouble again. So, and the same is true if we do this with a box. Okay, so this is a typical bounding box or bounding sphere, or in some way bounding volume intersection test. Now the question is, how does that perform, right? Let's say I've got a ton of objects here that I want to render, a lot of docs, I think. So, and what's the complexity of that, right? And well, I guess it's pretty straightforward. When we have an intersection, it takes a little bit more time, right? It takes, say, a million triangle tests plus one sphere test for one of these docs. And for 1,000 docs, it's, in the worst case, 1,000 more sphere tests plus 1,000 times million more intersection tests, which is a billion, I guess. But when the ray doesn't hit the sphere, I just have to do one test. Okay, so in some situation, it actually makes the thing a little bit worse, and in some situation, it makes it a little bit faster, or significantly faster. Okay, now, and I've already pointed out here, one situation significantly faster, and one situation, well, just a little bit worse. So that's good, right? So this means that in many cases I can gain a lot, and in some cases I lose a little, which in some way makes this thing faster. And that's the case, yeah, it's actually significantly faster, but, and this is the big but here, that's where I want to be, but in essence, I didn't change the complexity. Okay, I didn't change the asymptotic complexity, but it's again just a constant that I fixed here. Why? Because, well, there's still situations in there for some pixels, maybe, be it even 1% of the, be it only 1% of the pixels, but still for, say, 0.01 times p times, well, we still have to do times n, okay? Because we still have to check all of the triangles for some of them. And since we drop all lower order terms, and since we drop all constants, we end up with O of p times n still. Okay, so this again reduces the time it takes to do the total rendering, but it's still only fiddling with a constant. But that's actually not bad. it's just a side note here, right? So just like the intersection test only reduces the constant, this also only reduces the constant. But, and here comes another but, we can do better. Okay, there's actually a way to reduce the complexity here, even in the asymptotic case. Okay, and that is by introducing bounding volume hierarchies, or BVH in short. Okay, so what's the idea here? The idea is that instead of computing a bounding volume just around every object, we can throw those into a hierarchy. Okay, so and here's a simple depiction of that. Say we have a bunch of objects, and those might be simple polygonal objects or whatever. I can compute bounding volumes around them, say bounding spheres, or in 2D bounding circles. And then I can take those bounding circles and combine a few into bigger circles and combine them all into one circle. And I do this in kind of both directions, upwards, so that I end up with one big circle that encloses everything, and downwards, even those objects here, I can break them down into smaller objects. So I can, for instance, take my teapot or my bunny and just select sets of 10 triangles and throw them into circles or spheres. Okay, so just want to make sure that at the bottom level of this tree, what this ends up being, the bottom level of this tree, there's only a constant number of triangles. Okay, so I break this down up to the point where I end up with just very few, meaning a constant number. Very few can be 10,000, but it has to be a constant number of triangles. Okay, and then what do? Well, if I want to compute an intersection, again, get myself out of the way here, if I want to compute an intersection with that structure, with that tree structure, which it really is, because every bounding volume breaks down into a few more bounding volumes. Okay? You recursively descend that tree. So we first compute the intersection with a circle in 2D or the sphere in 3D that encloses everything. If I get a miss, great, done. If I hit, I check all the subtrees. Okay, then again, if I miss, great. If I hit, I check all the subtrees, so on and so forth. And the hope is, and that usually happens, that this happens on average, that I only end up having to follow a constant number of passes through the tree until I get at the bottom. And since the bottom leaf by design contains only a constant number of triangles, this is also constant. So bottom line is I get constant paths times constant work at the bottom, which is a constant. And how long is the path? Well, it's logarithmic, right? If I manage to reduce, say, the number of objects inside each of those spheres by, say, half, right? Let's do this as a simple binary approach, right? I cut every sphere into 2 spheres, so on and so forth. Then this has a logarithmic depth. Again, if you want to know details about this, well, this has all been discussed in data structures and algorithms, which is, by the way, available as a stream on YouTube. So what we end up having to do is some n log n work, okay? Some log n work, not n log n, right? It's log n times constant, okay? And what's our logarithm in what? Well, logarithm in number of triangles. And if you do this for each pixel, you end up number of pixels times logarithm of triangles, okay? Assuming that you've computed this bounding volume hierarchy, which in turn, and that's sort of the bad news here, requires sorting, so it's n log n. So what this boils down to is, if you can compute your bounding volume hierarchy and you don't have to update that, which effectively means you need a static scene, then you can reduce the complexity from linear, or from number, let's be more specific here, numbers of pixels times numbers of objects, to numbers of pixels times logarithm of objects, which is a huge difference, okay? So remember, numbers of objects is gigantic. It's potentially trillions. The logarithm of trillions is significantly smaller than just trillion itself, right? I mean, it depends on the logarithm, but obviously there's only a constant difference here. So this makes a huge difference once you've computing this bounded volume hierarchy, okay? Now you might argue, well, most scenes aren't really static, okay? So the good thing is, if I change the viewer's position, this can remain, okay? So when I mean static here, I literally mean the scene doesn't change, okay? Good, but the scenes unfortunately aren't really static. So what do we do now? Well, 2 things. A is you give up and you recreate this whole process, and you realize, okay, it's n log n, so it's not cool, because that is obviously slower. And that brings me back to my initial argument of this worst case complexity being a big deal. So even if we have to do this only every now and then, we end up with frames that instead of log n suddenly require n log n. And again, n is trillions. So that would be completely unacceptable. That would mean you have a game that runs smoothly, then you're stuck for a second in a frame, and then it runs smoothly again. You don't want to play that. Okay, so that wouldn't work out. So there's another solution, and that is, well, again, accept errors. Accept small errors that if object shifts around, that your computation is not 100% accurate, but hopefully you won't notice. So that's an approach that you could do. And then instead of updating this, doing this n log n, you could spread this over n frames, right? I mean, you have log n per frame time, and then you could spread your recomputation over n frames, and then you again would get into a sort of updated, it's still not a valid state, but an updated state. But unfortunately, n is trillions, right? So this will take forever again. So it would probably take forever for you to get an updated tree state. So also doesn't work very well. So what works better is what's called incremental updates. So I mean, usually when you play a game, it's not like you have a situation where the entire scene kind of completely changes. Well, there might be a situation, I don't know, where a universe explodes. Okay, well then yes. But other than that, there's probably some character kind of moving around, another one is being blown up, another one disappears, or whatever. So if you carefully track all of those interactions, you end up with having just to do local updates, and those can be done pretty quick to the tree. Okay, so that's sort of the basic idea of keeping these bounding volume hierarchies sort of updated quickly by computing them once. So that potentially takes a very long time. but then being able to do this very quick. But it's a non-trivial process to do all of these tracking things. Okay, so but with that one, we can actually get to an n or p log n complexity. Okay, at least, well, practically, not theoretically, practically. In theory, again, you can create situations where a complete update is necessary, and that's when this would break down, which is also the reason why like pure ray tracing isn't very popular for games because of these issues and the fact that it doesn't map very well to hardware. So now one kind of final set of remarks here. What types of bounding volumes are popular? And there's basically three types. There's a lot more, but the basic types are spheres in 2D circles, and then axis-aligned boxes and object-aligned boxes. And then technically you could come up with something else that approximates an object better. If I throw those four things, so spheres, axis-aligned, object-aligned boxes, and something better onto one slide, I would say that from the left to the right, they approximate the object better for a normal object. Right? They approximate the object, meaning an average object. They approximate the object better towards the right. Right? You have less empty space, so there's a potential hit gets called rarer and rarer. But the construction and intersection test is more complex towards the right. You have to find sort of a trade-off where you want to be in between. Obviously, there's situations where, for instance, the bounding sphere is good if you're dealing with spheres to start with, yes. But for general objects, bounding spheres are easy to compute, easy to maintain, and easy to intersect, but give you the worst kind of ratio of calls where it says, yes, there might be an intersection, but there isn't really one. Okay, so then it's a tighter fit. Now, there's other interesting things about these spheres or about these objects. I said bounding spheres are easy to compute. I already said how to compute them. I said they're not very great when it comes to actually figuring out whether you have a positive intersection or not. They give you a lot of false positives, no false negatives. None of these give you false negative, right? But they give you a lot of false positives, saying, okay, there is an intersection while there is not one. But there's another set of cool things. So for instance, if you move your object around, right, you can also move the sphere around. So the sphere doesn't have to be recomputed. If you move your object by 10 units to the left, you'd simply move the center by 10 units to the left and you're done. Okay, so and the same is true if you rotate an object. So obviously a sphere is rotationally invariant, meaning if I rotate it, nothing changes. So if I rotate an object, I have to do nothing. If I scale an object, say I blow this up by a factor of 5, all I have to do is scale the radius up. So as long as those transformations are rigid, meaning translations and rotations, or they are scaling, so these things, rigid transformation and scaling, which are called, what is the term again? Ähnlichkeitsabbildung. So I can't remember the English term, but in any case, those two things combined can be easily mapped to the spheres. Okay, similarity mapping. So that's the English term. Okay, so as long as you do similarity mappings, you only apply them to either the radius or the center, and voila, you're done. That's great. Those are the good things about spheres, and this is what a hierarchy of these spheres might look like. Okay, notice how here again we waste a lot of space, and when we have a certain overlap as well. So if we compute one intersection, we might have to traverse through multiple of these paths, but it turns out those multitude of paths is very small that we generally need to traverse. So the next one are axis-aligned bounding boxes. So again, those are usually tighter. They're also pretty easy to compute, right? What's an axis-aligned bounding box? Well, for that, or what does it take to compute that? Well, we only compute the minimum. We run once over all vertices. We compute the minimum x, y, z, and we compute the maximum x, y, z. So all separate, right? Separate x, separate y, separate z. So we get 6 values: the smallest x, the smallest y, the smallest z, the biggest x, the biggest y, the biggest z, and those happen to be the corners of our bounding box. So it's again trivial to compute, but it takes more. There's more situations where we need to do complete updates. So for instance, if I rotate the object, I need to update that, right? So if I rotate the object, my axis-aligned bounding box changes. Meaning I have to again run through all vertices and figure this out again. So it's again a linear process. If I translate the object, it's nice. I just translate those 2 corner points, so that's good. And if I scale again, this is also no big deal. So this is also just an application to those to the vertices of the bounding box. And here's a hierarchy of those boxes. So long story short, easy to compute, probably even easier than the sphere. But the intersection is a little bit more tricky. So basically you end up having to do a face intersection with 6 faces. So give or take, it's 6 times the work than the sphere. It requires a little bit more work when it comes to changing the object, and rotation is costly, but it's tighter. So those are kind of the pros and cons. Now for the last thing, object-oriented bounding boxes, here for the same object, I just rotated a little bit. So here are the object-aligned bounding boxes. You see they are bounding boxes, but they're not necessarily axis-aligned. They just, you kind of put them in a way that they fit the object best. Okay, so what are the pros and cons here? Well, the con is that it takes a little bit more sophistication to figure out how to place them, right? Because you basically need to find the orientation. Okay, more on that in advanced image synthesis later next semester. But bottom line, you can do this. It's just more computation intense. It's not a complete deal breaker, but it takes some work. It's fixed in object coordinates. That means that if you now rotate an object, cool, you just rotate those those object-aligned bounding boxes. So rotation is easy, translation is just a translation, and scaling is just scaling. So long story short, just like with the spheres, you just apply the similarity mappings to the bounding box itself, and it'll just stay with the object. So that is fast. So if they are better fit, if it's theoretically a little bit more work, but practically not such a huge deal to compute them, and if they're easier to rotate, so well, and they're good at rotation, that's what I said before. So what is then the reason not to use them if we've got all of those positive things here, and that thing, this one negative thing, is not such a big deal? Well, the big deal is, while there is an efficient intersection test, it is still slower than the intersection test with an axis-aligned bounding box. Okay, so we do have an efficient test, but it's more work. Okay, so the test is the hardest, and the pre-process is a little bit harder, and you gain something in between. So what you can see is, for all these 3 things, and if you include any other thing as a 4th application, it just continues this theme that you get from simple to more complex to, well, not so great fit but easy to compute, to super great fit but harder to compute. Okay, and this manifests itself as, well, you need to spend more work in the process of descending that hierarchy, but you don't need to descend that hierarchy that often. So which one's the best? How can I make this long story short? I can't. It turns out this depends. There's no clear winner here, really. So it depends on the situation. It depends on what operations do you apply to your object. So it really depends a lot. It even depends on the hardware that you're using. So for some hardware, one works better. For some piece of hardware, the other works better. So long story short, they're all kind of good at bad. So if you don't have a clue, just pick one. Pick the one that's easiest to implement, I guess. Pick the spheres. Okay. So those are bounding volume hierarchies. Okay, BVH. A completely different approach is what's called spatial subdivision. Okay, so when you stick back a little bit now, again, we're in this how can we do fewer test regime, but now we want to use a different approach to achieve those fewer tests. How do we do this? And now it looks like it's almost the same, but it's not. So this time we will not break the object into boxes, but we'll break space into boxes or other things. Okay, that's very different, and indeed it can be combined with the bounding volume hierarchies, but it's still a different approach, right? So here I take the entire space. So this is my say this square here is my space of everything in the scene, And then I simply separate this space into 4 subspaces and then continue to do this, for instance, here. And in my example here, the objects nicely fit into the 4 subspaces, okay? This might not always be the case. So I might have this situation here where it doesn't fit. And there's a solution to that, but I'll just pretend this doesn't happen here. In this lecture, I'll just pretend it doesn't happen, right? The simple solutions are, well, throw the object into both things or split it into 2 objects. And both have their pros and cons, but I'll just pretend that thing doesn't happen, okay? So we'll just split the domain up, and we'll then throw the objects into the subspaces that are generated. So how can we split things up? So first thing is we can use a uniform grid, meaning we just split up the world in regular grid cells. And then when we raycast or ray trace or traverse this, we can simply, instead of going over all objects, we simply go through all cells. So we have a certain starting point, right? So this is where we start our rays, and this is inside a cell, okay? This can be computed very efficiently. It's just a modular computation if it's a uniform grid. And then we simply check, okay, which one is the first cell that we enter, which is this one here. Let's just take one specific, let's take this right here. Okay, so this is the first cell that I enter. I check, is there anything in there? So because it's a data structure, I can simply ask it, like, is this cell, does it contain something? If yes, give me that something. Okay, the answer is no. We're immediately done. Proceed to the next cell here. Okay, we get nothing in there, nothing in there, nothing in there. Okay, that's all quick. And here we get, oh, well, there's one object in there. We compute the intersection test, find something done. So what have we done? Well, we've done a lot of pretty quick recalls and then just computed one object ray intersection. And the same is true for other rays here, right? So this one here. So here we got, let's see, here we got one that gets nothing, computes an intersection test, but fails. Continues to the next one, again, computes an intersection test, fails, proceeds to the next one, intersection test fails, proceeds to the next one, is empty, and exits. Okay, so sometimes we need to do more than one intersection test, but as I said before, so these concepts and sorting are related. So in essence, by first computing this grid and figuring out which object is in which grid cell, we then produce a data structure that allows us to do sorting. Because what we do here is really, we receive the objects in depth order, right? So if I go along this ray here, I get all the potential intersection tests, but in depth order, which means if I find one intersection, I can immediately stop, right? Or at least once I've computed all intersections with the objects in that cell, I can stop, and I don't have to consider another cell because that has to be behind the other one, okay? So in a sense, this is an auxiliary data structure to do sorting, okay? If you look at the details, you'll see that there is an O of n log n hidden in there somewhere. But not considering that so much, let's just look at the properties of that thing. So first of all, we need to throw things into grid cells, which is, let's just for simplicity's sake assume that every object is just a point, which is trivial. We just go over all objects, figure out what grid cell do they belong to, and just throw them into, say, a linear list or something. Okay, so that's not a big deal. And then later on, figuring out in which cell we are is basically just rasterization. It's just turning a line into a set of blocks, which is also easy to do. Now, those are the good things. So what are the bad things then? Well, the bad things are if your objects are non-uniformly distributed, meaning you have a ton of things sitting in one place, and then you have a lot of empty space, and then again, a few things sitting here. This is going to be bad. And simple example, you have a room. You have a simple room, you have a computer game, or you have a virtual environment where there's a room, and there's a table, and there's objects on the table. There's a lot of empty space, right? In your normal room, your volume is pretty much empty, except for, well, a few places. And let's say there's this dinner table that has cups and plates and whatever sitting on the table. So you end up having some of these cells contain a ton of data, lots of triangles, and a lot of these cells being empty. Okay, but still you need to store all those cells, right? Well, if you store linear lists for each cell, then a lot of these cells will have null pointers. To be a little bit technical here, but still you need to store all those null pointers. Okay, and then the question is, how big do I make every cell? right? You generally want to make those cells pretty small, because when you hit a cell, you have to then compute an intersection with everything that's inside the cell. The smaller the cell, the more likely it is for this cell to contain a smaller list. However, if you take your room and you maybe take a regular room here, right? Take the room I'm in here, so this might be 5 by 5 meters or so. Oh, it's actually smaller. It's maybe 4 by 4 meters. Okay, so I'm in a 4 by 4 meter room here, and if I make a cell size of 1 centimeter, right? This is 4 by 4 by maybe 3 meters in volume. If I break this down into 1 centimeter cells, I get a ton of cells, right? I mean, you do this 400 by 400 by 300, right? You get a pretty large amount of cells. Right? That takes a lot of memory, and a lot of memory just simply means a lot of storage requirements, but it also means a performance impact, right? Because it's probably going to be bigger than your cache. It's probably going to be bigger than even your main memory. So you might have to, inside a frame, right, which you want to do 30 times or 100 times per second, you might have to read data from the hard drive, which is totally prohibitive. Okay, so large data structures are a huge deal for performance as well. Now, if I make my cells bigger, I save memory, but then I have to do more intersection tests. So the resolution of the grid is really a big deal. Okay, so what would be more beneficial would be, well, a data structure that has more cells near my table, in my table example, and fewer cells anywhere else. So I want to have sort of a more flexible, adaptive data structure, right? And there's 3 types of very popular data structures that do exactly that. And those are octrees, KD trees, and binary space partitioning trees. Usually you could just call this BSP, but technically it's also a tree. Okay, so let's look at the first thing, the octree, and let's look in particular at a quadtree first. Okay, so what's a quadtree and what's then an octree? Well, quad means 4, oct means 8. Okay, so in 2D the thing is a quadtree, and that's what I've just presented before. So a quadtree means you take your space and divide it into 4 quadrants. Okay, and you make this division always the same. It's always through the center. Okay, and then you decide whether you want to further subdivide those quadrants. Okay, so here I figure, okay, it only contains 2 objects, this one and that one. Okay, so we'll stick with it. Say I subdivide when I'm getting more than 2. So here I stop. Here I only have 1, I stop. Here there's none in there, so I also stop. So the only thing that needs to be subdivided, this one here, because it contains 1, 2, 3, it contains a total of 7 objects. So I subdivide this again, here and here. I find this one's empty, this one contains only 1, this one contains 3, and this one contains 4, so I continue to subdivide them. Bottom line is this is what I get. Okay, so I still get sort of a semi-regular structure here. So it's still very structured in the sense that I always split up along the center, but I allow to stop. And what I actually get is I get a set of nested regular grids, right? Not nesty, nested. Okay, so the first regular grid is just has this spacing here, right? And then I get a regular grid nest in that one with half the spacing, quarter of the spacing, so on and so forth. So in a sense, it's a set of regular grids where some of those grids are just defined in some places. Okay, so that means the traversal structure is very similar to the regular grid structure. Okay, so it's still very simple, and I don't want to go into too many of the details here, but it's sort of a nice trade-off between regularity and more adaptivity. Okay, welcome folks. We're doing spatial acceleration structure here, and currently talking about quadtrees. So the next step will be octrees, right? If you extend this idea to 3D, you get octrees. Okay, and the reason I don't explain octrees is first is they're hard to draw. Right? In 3D, I actually get all this occlusion, but the idea is really you do your quadtree and then another second quadtree, right? Splitting at the front plane. And this gives you an octree, and here's an octree for the Stanford bunny, okay? And since you still really can't see anything, here's a little bit of an animation. So this is what you get when you just let a bunch of points cluster together and you build a dynamic octree around those. And here I look along one axis, and I've colored every new tree cell in red that is created. And as you can see, this thing grows when this dendrite grows, And you can see how new cells are created when we need to split them. I think here we split a cell when we have more than 5 objects in a cell. And I can also run an animation here, so I'll just get out of the way. So this is the very same thing, but now not axis aligned, but will actually let the object rotate. So you get a you get a better understanding of, or maybe not due to all the occlusion, but you might get a glimpse of how these octrees grow, right? And you can see how all the empty space around the object is is just very few big cells, and then there's more and more cells around the structure. So they approximate the structure pretty well. Then with these octrees, you can do all kinds of things. For instance, traverse them, which is what we need in ray tracing. Traverse them pretty quickly. You can also do a neighborhood search efficiently. It's a little bit more tricky. The construction is also relatively fast, so the update is pretty fast. So yeah, where's that from? So we've actually coded that live in one of the late night coding sessions, or in actually a few of the late night coding sessions. So if you're interested in the implementation details, or you want to get the source code of that demo here that you see, it's actually pretty simple, or it's relatively short code. You can just watch my late night coding series and just look up. I think we literally call that part octrees or dendrite growth or something. Okay. So I guess your script doesn't work. So okay. So those are octrees. Okay. So and again, the traversal is very similar to regular grids. You just basically have to figure out what is the size of the cell that I'm currently in, then pretend it's a regular grid, find the next one. If that is subdivided, just take twice the resolution, and again do a regular grid traversal. So this is why I'm not going to go into details here. It's just a modified regular grid traversal. So just to kind of look at a specific example here. So if we follow an array through a regular grid, on the left you see that the gray cells are the one that I have to look at. And if I have an octree here for the very same data, there's significantly fewer cells that I need to look at. That's the bottom line. I might have to check more objects, right? Notice how I have to check that sphere here or circle, and I didn't check this here. So that can happen, yes. And the same is true for this one here. But in general, in particular, if you see it's very non-uniform, so there's a lot of things going on in one place and few things going on the other part of the data, then this octrees are more efficient, but they take a little bit more work to build. But they save a lot of memory, and as I've mentioned a few minutes ago, saving memory in high-performance environments means saving time. So this is usually the same because you run out of cache easier with bigger data structures. You run out of main memory, you have to go out of core, so it's a pain, and slows things down considerably. So with that, we got a pretty nice kind of trade-off between adaptiveness and speed. And now let's move kind of along this kind of line of adaptive structures and easy to do structures, fast structures. Let's kind of go to the opposite end. Let's look at the binary space partitioning trees, or just binary space partitioning. What does that mean? It's basically the idea of a binary search tree extended to more dimensions, 2D, 3D, so on and so forth. Okay, so let's just go to an example right away. So here's my scene. A, B, C, D are 4 objects in a scene, and I want to look at those. And what's a BSP? A BSP, binary space partition, is simply taking planes and cutting the world into 2 sides. Okay, so I start with plane 1, and that separates AC from BD. Okay, so I just cut the whole world. 2 planes. It works for any dimension. We end up with hyperplanes, but let's just do this in 1D, then our hyperplane is just a line, or in 2D, then the hyperplane is just a line. So I cut this into 2 subspaces, and then I take the 2 subspaces, the one on the left and the one on the right, and again I separate those by 2 lines, or in 3D by 2 planes. Okay, and what I then get is, well, a structure that has separated all the 4 objects from each other by the means of planes. And I can say that this here is kind of the same, or it's a similar representation. Okay, instead of writing this as an actual depiction of the objects, I can simply write this as a tree and say, okay, well, if there's first my separation plane P1, and then if I go to the, say, to the right, I have this subspace that is again subdivided by P3, and then if I go to the left, I end up with B. Okay, so if I kind of tilt my head, B is to the left of P3. Okay, so what is this good for? Well, first of all, you can imagine that this is that an octree is just a very specific version of that one, where I happen to place my planes always in the center of the space. So a BSP is a generalization of octrees in that sense. And how can I use it? Okay, let's just try to render a scene. And remember, one thing that we sort of wanted to do is we wanted to depth sort the scene to be able to render. We want to know what's in front and what's in the back. Okay, things in front should be processed first, and then if they're opaque, we're done. If we're dealing with transparent scenes, then we need to do something else. More on that later. Okay, and let's figure out what's the closest object. For this one, if we're in a BSP tree, we take our viewer's position, the start of the array, okay, and we figure out in what, where are we in the tree. That just basically means descending the tree once. So we simply look, are we on the left or are we on the right of that plane? So here for the I position, we figure out, oh, we're on the right of P1 and we're on the left of P3, so we end up here. So and then what we do is we first process whatever is in that subspace, okay, which happens to be P3. And if that's an actual sphere we want to render, here it is. And then we proceed to the next subspace that is a sibling of the one that we're in, which is D. And then we step one up, look at the other sibling, which is this space that is now subdivided by P2, figure out where are we with respect to P2. We're on the right? We now need to tilt the head the other way, right? So we first process A and then C, okay? And with that, we get the depth order, okay? Oh, what's ray tracing? What is ray tracing? It's not a thing I can explain in 10 seconds because I did this in my I did this in about 1 hour last week in the stream. Ray tracing is a rendering method. It follows rays from the eye through the scene and checks what do these rays intersect. And if you repeat this process for every pixel and you figure out what pixel does intersect what objects, you can figure out what this ray sees and what you get. Okay, good. And with that one, we can get our sort of depth sorting. And if we get depth sorting, if we can process things along the depth, we can, as I've argued maybe half an hour ago, we can significantly speed up our intersection because we have to, we don't have to look at all objects. Okay, so how do we construct BSP trees? That's kind of the big deal. Okay, so we have to figure out where do we need to place the planes, and for that we have a lot of choices to make, right? We can basically place those planes everywhere, which means we have to find a point, a position for the plane, and we have to find an orientation for the plane, and we have to find the best one for that plane, which is a lot to decide on. Okay, where are those planes supposed to be? And that's maybe not even unique. So what this boils down is a minimization problem. So where's the best position is generally a minimization problem, minimizing some sort of cost function. And then we basically pick the position with the lowest cost. So and that cost function might be, okay, well, we want to intersect as few as possible objects. We want to have a best as possible split. So maybe half of the objects on one side, half of the objects on the other side. We want to split space best, half the space on one side, half the space on the other side. I don't want to explain this here in the context of BSP trees, but I want to explain in the context of another type of tree, which is in between BSP and octrees, which is called a KD tree. If you're clever enough, when I give you the cost function for the KD tree, you'll see that you can explain this. You can apply the same concept to BSP trees as well. So when I explain the cost function of KD trees, you might want to go back here and check, okay, what are the tiny little things that I need to change to also get BSP trees to work? So the idea is similar. But what is a KD tree? A KD tree is in between octrees and BSP, and it's a specialization of a BSP, or it's a generalization of an octree, and the idea is simple. We fix one thing, and that's the orientation. Okay, for octrees, things were always oriented perpendicular to axes, and the position was fixed. For BSP trees, we were allowed to do everything. We could we could choose any orientation in any position. For a KD tree, we can choose any position, but we'll fix the orientation. It's always going to be X, Y, Z. Okay, so it's kind of in the middle. Okay, so and there's different variations of the theme. So for instance, you could say, well, you can choose, it's always going to be X, Y, Z, X, Y, Z, or you can say, well, I can do an arbitrary number of X, perpendicular to x-axis, split planes or not. So we'll just say here it's always x, y, z. And here's an example of a scene being split up, into a number of different octree parts. Okay, so the trouble is, again, where do we place those things? So we've now fixed the orientation, but this means we have an infinite amount of, well, positions to choose from. Well, the positions are obviously just along one axis, so they're at least one-dimensional, but there's still tons of things to choose, right? If this here is my scene with just a few objects, okay, and I've just computed bounding boxes around them, so we might want to split them here, or here, or here, or here. Well, there are tons of different choices to make. One simplification that we can do to at least get this infinite amount down to a finite amount is we could say, well, it sort of only makes sense to split at axis-aligned bounding box locations, right? Whether I split here or here or here or here will not make a big difference until I get to this point where I have different objects in my cells. Okay, so and yes, if you've attended advanced image synthesis, that builds on top of that. So yeah, there are certain similarities because I continue to talk about this. Yeah, so obviously there's things that are similar. So if you do that consideration, you could say, well, okay, at least we get this infinite amount down to finite choices that we have to make. Okay, so we can either place the plane here or here or here or here, right? So we'll still get a ton of different choices, but we'll at least limit them to a finite amount, meaning we could write a loop and loop over all. So this is now possible with that thing. Okay, so that's the first consideration. Now for this cost function thing, and let's again get myself out of the way. So what's this cost function? And we have a minimization problem. We want to figure out which one is the cheapest, which one is the best position to choose. And how would we choose that? Okay, so one way would be to iterate over all possibilities along one axis. This is now a finite number. Compute some costs, whatever the cost is. More on that in a second. And then pick the one with the cheapest cost. And that's really it. That's it. So how do we pick the cost? Okay, let's take this scene here. Okay. So, and I've chosen a scene where the distribution of objects, in this case just a bunch of triangles, is very non-uniform, which is really the situation where you need adaptive grids. Okay, and this means we have very few, meaning in this case one triangle on the left and a lot of triangle on the right. So where would we place where would we want to place our split axis if we want to be perpendicular to the x-axis to start with? Okay, so one thing we could do, we could place it here. Admittedly, that's not on a bounding box, but just for argument's sake. Okay, this would be one way. We could split in the middle. What would be the effect of that? Well, we would split space nicely in 50-50, which sounds like a good idea, and that's exactly what an octree does. Okay, so that would mean that half the rays, if I would look into this direction, half the rays would go into one part of the tree and the other half of the rays would go onto the other part of the tree. Or if we approach this in a more stochastic fashion, we would say 50%, the chance is 50% that we traverse the left, and it's 50% that we traverse the right. Okay, which is generally a good thing, right? If you design a tree, you want this to be uniformly distributed. However, there's one catch, and that is, I mean, 50% of the rays go to the right, but they do a ton of work, right? This tree is going to split up a lot of times, and 50% have to do almost no work. Okay, which is bad. Okay, this is not so cool because it means we have non-uniform work, and the performance is always dominated by the worst thing that we do. Okay, other idea. Let's split at half of the triangles. Let's see that half of the triangles are on the left and half of the triangles are on the right. What's the effect? Well, the effect is now all of the rays that run through this data structures do the same amount of work. We have a lot of arrays that follow this path here, and we have significantly fewer arrays that follow this path here, but all the arrays do the same amount of work. Okay, which is again good. The question is, can we do better? And it turns out, yes, you can do better, because, well, as I said, there's a few arrays here that do the same amount of work as the many arrays here that do the same amount of work. So what we can do is we can, I'm just hand wavy first, we can shift this plane a little bit to the side, then we've got few arrays that do more work and a lot of arrays that do less work. But didn't I say in the beginning that this is a stupid idea? No, I said it's a stupid idea to have half of the arrays do a lot of work and half of the arrays to do fewer work. But few arrays to do a lot of work and a lot of arrays to do less work, in summary, you might still have this dominating factor in there, but on average, that gives you the best possible average. Okay? So how can we find this position so that we get this kind of best trade-off that the work is reciprocal to the chances of ending up there? Okay, so if you do 100 times more work, but the probability is just 100, then on average you end up with 1. Again, stochastically speaking, right? So what this means in reality might be a slightly different story, but if you do enough arrays and you process them in a nicely parallel fashion, then this might actually work out. Okay, so let's try to get the stochastic complexity, the stochastic average. Let's try to minimize that. Okay, and this is what a so-called SAH, or in long, surface area heuristic, does. Okay, it takes exactly into account, like, what's the probability of going into one way, and what's the work that we need to spend in that way. Okay, so we define the cost function as follows. Let's see, how can I get this? Probably here. It's the best way to place myself. Okay, so here's the cost function. It's made up of 3 terms. Some traversal cost, T, some cost for one side, and some cost for the other side of traversing a tree, right? So, and this is probably always true, right? You have some cost that it takes to get to that point, or to unpack that point, to get that certain part of a tree from memory. This is this constant traversal time, TT. And then there's a certain probability that I end up in one side, and that's PA. Okay, PA is the probability that we go to side A, and then we have to do a certain amount of work on side A, and that is proportional to the number of primitives in that side. Okay, so that's exactly my number of triangles times probability thing here, and then I need to multiply with some other TI cost, that is basically the work I have to do to figure out that I'm in this side. Okay, so this is kind of a constant work that I have to do inside that tree cell. Okay, so and then I might also have to go the other way. Okay, and the other way is then the probability that I go into the other direction times the number of objects times, well, again, some intersection that I do here. Okay, so this is a very general term. How can I make this a little bit more specific? And the number of objects is easy. This is a number of objects. I can literally read that from the tree. TI and TT, I think that I can compute. So I can literally run a computer and let it go through levels of my hierarchy, compute the time in seconds it takes for the traversal in the hierarchy. I can measure the seconds, how many seconds or milliseconds or nanoseconds does it take to figure out I'm in the left side, to figure out I'm in the right side. So those are things that I can time. So the big deal is really P. What's the probability I end up in the left or in the right side? And this is where heuristic comes in. So this is where this is not accurate. It's just a guess. It's an educated guess. That's what heuristic means. Right? And I can approximate those probabilities by, well, the surface area. That's why it's called surface area heuristic. And how do I approximate them? It's simply SA divided by S and SB divided by S. Okay, what are SA and SB? S is the surface area of this cell that I'm currently in. Okay, so, or this box in 3D. And SA is the surface area of one side, and SB is the surface area of the other side. Okay, so if we go back to the previous slide, then this is a 2D depiction, and the surface area of this 2D thing would be, SA would be the whole, the complete blue area here, and SB would be this area here, right? and SA would be this area here. So the two obviously sum up to 1, so it's good. It's a probability. That's always great that the probabilities sum up to 1. And the probability that I end up going this side is, well, if for a random ray, it's, well, the entire space dividing just the space that I'm looking at. Okay. In 3D, those end up being boxes. Okay. So this is an area of a big box and areas of small box, but still the idea holds that when I look from an arbitrary direction, the areas of the box might be a good approximation. I say might be a good thing because the boxes might be behind each other. So you see there a situation where this breaks down, right? So this only works if you're looking, this only works perfectly if you're looking kind of perpendicular to the direction of split. Right? In other direction, this breaks down a little bit, but it's a pretty good approximation of the actual cost because the problem is here, this PB needs to hold for any direction, and it's a pretty good approximation for that one. Okay, so what you do then is you compute this cost C for any possible split, and you simply take the split that has the smallest C. If you do this for this scenario here, and I said these spatial accelerations are always hard to draw because you get all this occlusion. So let's again do this in some sort of a slow animation here, just a few frame by frame things. So if I do this here, I would place the first split plane here. So this is exactly running SAH over this area. Then the second split plane would be perpendicular to the x-axis. So we started with perpendicular to the y. Second split plane would be perpendicular to the x-axis, of course, in every subspace. And since the top subspace only has 2 objects in it, we just choose one side. The bottom one is now the more interesting thing. So then we split along Z or perpendicular to Z, and on the top there's no Z split necessary, so we'll continue to the X split right away, and then again comes an X split here, and now it starts to get a little bit messy here. But you see there's more and more planes coming in, and as I said, it's really hard to see anything. So even if you start to rotate that, I compute an animation with that as well, you can't really see much. But what the only thing that you can tell, which is really the important thing here, is you see how this kind of builds, it chops out areas around objects. Okay, and it does this in it chooses this kind of chop position so that the probabilities are uniformly distributed, or as uniform object amount weighted as possible. Okay. So what can be said in summary here, that is, if we take these octree where this KD tree, where this BSP trees, it's kind of similar to the bounding spheres, axis-aligned bounding boxes, object-aligned bounding boxes situation. Octrees and grids, I haven't put grids on this slide here, but they're kind of to the left of octrees, are simple, but grids aren't adaptive at all. Octrees are sort of semi-adaptive, KD trees are more adaptive, and BSP trees are hellish adaptive. Okay, so the more you can adjust to your scene, the fewer objects you're likely to chop through, which is good because they cause problems, which I ignored here. The better you split your world into 2 sides, but the more complex your computation, both of the tree itself and potentially the traversal becomes. So again, the question is, well, which one do we choose? Grids, octrees, KTs, BSP trees? And the answer is the same as before. I don't know. No one knows. It depends. It depends on 2 things. Your personal preference, really. So all of them sort of work. And again, architecture. So you might have a piece of hardware that has a support for octrees built in. So then you want to use those. So you're only dealing with constants here. Every time you're dealing with optimizations that are on a constant level, it becomes very specific or it might become specific to hardware. To give you sort of a little bit of an insight of what research has focused on, again, it's a very non-uniform landscape. So KD trees have been popular for a pretty long while. So people were like, oh, KD trees is the only way to go, and researchers working on accelerating particular ray tracing systems. And then it was suddenly BSP trees, and then it was suddenly OGG trees, and then people would write papers that would show that the previous idea wouldn't work out anymore, or here's a new idea, and suddenly that one's better. So long story short, it's very non-uniform. I can tell you what's currently the hottest topic is, and that's a hybrid approach between KD trees and bounding volume hierarchies. So you would use trees and then put, instead of the triangles into the trees, at some point you just put hierarchies of bounding volumes into the tree. And then, or the other way around, you can also do it the other way around. You have a hierarchy, and then hierarchy of bounding volumes, and then if you get below a certain level, you start to use trees. And both of them are used. But that appears to be right now kind of a nice approach, or a fast approach. But I wouldn't necessarily say that this is the same 5 years from now. So we might have some other variation of that theme again. Okay, but bottom line is what this results in is it speeds up the constant considerably. So it might make a huge difference. Again, 1,000 times faster is a constant, but it makes a difference, right? Whether it takes 1,000 seconds or 1 second, whether you get 1,000 frames per second or 1 frame per second, makes a certain difference for real-time application. And again, computer graphics is such an application, or at least in many situations, it's a real-time application. Okay, so that's Act 1. Act 2 is if you split your work up into pre-processing and processing on the fly, you might get better than number of pixels times number of rays. Okay, making certain assumptions about the scene, for instance, that it only undergoes certain transformations, or that it remains entirely static. Okay, so those are kind of the two things. That combined allows you to do an approach that is generally very costly, ray tracing or path tracing, which is either a variant of ray tracing or not, depending on how you view the world. But it might give you the ability to do this in real time. And this is what we see in modern AAA titles, that you have a certain hardware support for a certain number of ray tracing operations or path tracing operations, and that would allow you to do at least parts of the scene, or very simple scenes, using ray tracing fast enough so that you can run them interactively. Okay, so and as I mentioned the last time already, there's a lot of trickery involved on top of that. It's not just what I explained here. It's not just fast intersection. It's not just smart acceleration structure. It's also smart post-processing. So this realm that I didn't talk about, like how can we reduce the number of rays, is a very crucial ingredient to real-time ray tracing systems on current graphics hardware. Right? How can we not shoot rays for certain pixels, but still guess what those pixel values are supposed to be? And that requires very sophisticated post-processing filters, which are today based on convolutional neural networks. So you have filters that are based on artificial intelligence, which is really just matrix vector multiplication. So it sounds like artificial intelligence is really crazy, but it's really just it's really just linear algebra. More on that in the following weeks in late night coding. Okay, but anyways, so that's the state of the art in ray tracing acceleration, okay, which is today's first topic. Any questions about that before I continue for the next 30 minutes? It's got about 30 minutes left. Any questions? Not much going on today, so not many questions. If there are any at all. Okay, well then let's continue with our questions. So I guess everything's clear then. That's cool. So let's look at two other important topics that are very much related to what we've done so far, and that is shading and texturing. I've already explained shading. The ones that recently joined, shading is this process of filling out gaps in between data points. And that sounds very complex, but it's actually not that complex. It's if you have a model, the model is made up as a polygonal mesh. It's made up of points. Those points make up the mesh. And then if I draw those points directly and maybe just the connection between the points, I get a ton of voids in between. So we need to fill those voids, and that's called shading. It doesn't have anything to do with shadow or with light or with darkness. It's just filling things out. Again, the German translation is schraffieren. So that's probably the best translation that you can get. So, so we got these models that are sparse in a sense, and the same is true for a screen, right? If we do a screen, if we do ray tracing, we shoot rays, so we get points. We need to fill out voids in between. So we have in scenes we have the same sort of discretization going on. We have certain points where we know the values, and we have void in between, and we somehow need to fill those voids. Okay, so we got a question. The previous topic is there vertices which promote scalability similar to high? Yeah. Well, I'm having a little bit of a problem here with the infinite. So you need to be very careful with mixing. I don't know, mixing, let's say, marketing terms with reality. So technically it's not entirely untrue. So when you deal with very large data, and this is a topic of advanced image synthesis, I talk about large and also infinite spaces, how to handle those. But yeah, the one key concept is usually some sort of a hierarchical structure. Yes. So you're dealing with your immediate surroundings in high resolution, then your not so immediate surroundings with lower resolution, and then so on and so forth. Whether that's a KD tree or whether you want to choose an octree or a completely different thing for that particular purpose depends a lot on the type of data. But yeah, it's usually some sort of tree. I wouldn't necessarily say KD tree, but it's some sort of a hierarchical structure, and hierarchical structure is just another word for tree. Okay, yeah, so the answer is yes, sort of, I guess. I haven't looked at the exact details about Unreal Engine 5, but I know how to do large terrains. I know how to do large large data in general. As a matter of fact, that's actually one of my research topics. There's different different types of hierarchical structures that you use. Okay, so let's now go back to shading, unless there's another question. I mean, feel free to ask questions anytime. I'll just pause. So how do we render polygonal models? So here, that's a very big polygonal model of the David structure, Michelangelo's David, laser scanned at fairly high resolution by colleagues from Stanford. So they built a scanner and scanned this statue, so you can literally see where pieces of stone, of marble were chopped off, and you can view this as very much detail. So and that was scanned by the means of a laser scanner. So literally they shot a lot of laser beams and figured out where would they hit the surface. So that means you would get a bunch of points, and if you don't want holes in between the points when you later render them, you need to fill the void, you need to shade the object. Okay, to do that, specifically for a mesh that's made up of a bunch of points, such as this one here, you first need to, well, create the mesh. And this is something, again, that I'm not going to explain here, how to fill the void, how to turn points into triangles. So this is again part of advanced image synthesis. Or let me think. Did we? No, that's actually part of scientific visualization. In the lecture Scientific Visualization, I talk about an approach how to fill it. But let's just assume here we have a notion of having a grid in between. So we already know how to connect the points, but we don't know how to fill the voids. Notice that there is still a void here, by the way, but this is a different story. Okay, so given that we have that structure between the points, or the connecting structure, we want to fill the in between. Okay, so if we have a ray that passes in between points, we want to know what's the color there. Okay, and well, the only thing we do know is the color at the vertices, be this because we scanned it or because we specified it. Okay? And for those that followed this stream for a few minutes, or as a matter of fact, for over an hour, and now you say, well, sure, haven't we solved this problem? Haven't we just figured this out? Yes, and yes, we did. I'll get back to this in a second. But what we want to do is we want to combine the values from the vertices by the means of, well, interpolation. So can this even be entirely automated? Does it always have to be fixed manually afterwards? You mean, what exactly do you want to do automated and fixed? You mean filling the voids in between? That I'll actually explain. Once you've got the grid, once you know the grid, we'll do everything automatic. So nothing has to be done manually here. Creating the grid itself can also be automated, but none of this has to be done manually. You just have to know how to do it in an automated fashion. However, there, in particular for creating the grid, not for shading, but for creating the grid, there are ambiguities that you might have to fix later on. Okay, but back to shading. How do we do this process? How do we fill the interior of a triangle? Okay, so first of all, we need to know where is the point inside the triangle, and what I mean by that is that I don't want the position of the point. I want its position inside the primitive. Okay, I want it to be in coordinates relative to the primitive. Okay, and then I want to use that to compute the color, right? So for instance, if everything is red, like all the vertices are red, well, sure, then the point should be red. However, if the points are, say, red, green, and blue, then maybe it's not that trivial. Okay, well, how do we interpolate inside a triangle? Linearly. For instance, right? And that's again geometric models too. That's from before. That's basically linear interpolation along a line. We can do this inside the triangle, and I won't go over the details again because I just did this a few minutes ago, and it boils down to this interpolation between 3 points. We can build a simple linear function, and at least that point here, that image should look very familiar because I've shown that maybe an hour ago. And the bottom line is that you can simply use linear interpolation, meaning barycentric interpolation. Okay, because let me go back one slide here. This formula, a plus b times one x plus c times another, that should be very familiar, except that we previously said x is p1 minus p0 and y is p2 minus p0. But other than that, it's exactly a plus b times one thing that depends on one direction plus c times another thing that depends on another direction. So it's exactly the same approach as before, right? And that's, as a matter of fact, exactly the same slide. So is this one, so is this one. So this is just supposed to be a reminder, okay? So if we are dealing with triangles, we know how to fill the interior. We simply run barycentric interpolation, which is another word for linear interpolation. Okay, so what do? We take the point inside the triangle, we figure out its barycentric coordinates, alpha 1, alpha 2, and alpha 0, alpha 1, alpha 2, or u, v, w, whatever you want to call them. We take these 3 coordinates, multiply the quantities at the vertices, and we get the interior. Okay, done. Good. Lecture done. Not completely. What happens if we don't have a triangle, if we have a quadrilateral? Well, then I could go, what happens if we have a 5-sided thing and a 6-sided thing? Well, I don't want to go that far, but remember at the beginning I said we have to interpolate on the object, which is often triangulated, but we also have to interpolate on the screen, and the screen is usually not triangulated. The screen is usually made up of rectangles or squares, okay, pixels. How do we interpolate inside those? And it's not just the screen, there's also things such as textures, which are also often just regular grids. So we also need to figure out, we need a second ingredient, and that is interpolation inside a quadrilateral. That's another important thing. Okay, and how do we interpolate inside a rectangle, or in 3D inside a brick? It's the same idea, by the means of bilinear interpolation. The bi here is very crucial. Okay, it's almost like linear interpolation, but it's bilinear, which makes it non-linear. That's important. Linear operators are very cool things. They allow us to do a lot of really nice things mathematically. Unfortunately, this one isn't linear, even though it has linear in its name. So be very careful with that. So how does it work? What are all those colorful indices here supposed to say? It's actually a pretty simple concept. The idea, and again, if you followed any of my other streams, advanced image synthesis, visualization, you've seen that before. So this is actually a pretty straightforward thing. So what's the idea? We have, let's look at the bottom here first, okay? We have our primitive to be interpolated, okay? So this here is our pixel, or this here is a piece of a texture. More on textures later. So if we want to figure out a point inside that thing. So it's the same problem as with the triangle, right? We have a point inside the object, except that now object is a, well, it's a rectangle. In this case, it's a square, but it works for any rectangle. So what do we know? Well, we've got coordinates for the 4 points of the rectangle. And we got coordinates for the point that we're looking for. And we've got function values. I've drawn them here as height, right? You can also draw them as colors, but I figured, okay, it might be nice to think about this as a height field, which is, by the way, another application for this purpose here. If you have height fields that are often given as regular grids. So this point here has a function value that's, say, 2. This point here has a function value that's 1. This point here has a function value that's, well, I guess 1.2. And this here has a function value of 1.8 maybe. Okay, so, and I want to know what's the, well, function value of this point here in the center. What's f of x, y? And again, I want to do this by, again, smoothly interpolating inside this thing. Okay, so this is what this image is supposed to be. So it's a question, what is this? Now, there's a few lines here that I haven't explained yet, which are these here, and that's exactly kind of the solution to the problem. How can we interpolate along a line? Well, we can interpolate along a line linearly. If you forget about all this and just pretend there's just 2 points here, and they have a height, and if we have 1 point in the center, and this also has a height, we want to figure out this one. Or let's do it at the front. Same problem here, right? 1 point has a height, another point has a height, and I want to know a point in the center. What is its height? Well, I can just draw a line in between the two and figure out where does this line go here. Same at the back, right? This point has a height, this one has a height. This one here I can also choose what's this height. And the same on the left. You get the idea. So I could do this at all 4 sides if I wanted to. How do I do it in the center? Well, I cleverly combine things. So I first do this in the front. I get this point here. What do I choose? I simply choose the x coordinate. So I project the x coordinate of my point in question to the front. Okay, and I figure out this point here. I project the x coordinate to the back. I get this point here. And now I got 2 coordinates here. Well, now I use the y coordinate to interpolate between these two and again, then get this point. And this is why it's called bilinear interpolation, because conceptually I do a linear interpolation along the x-axis and along the y-axis, which means 2 axes, which means bi. Okay, this is where the bi comes from. Okay. As a matter of fact, I do 3 interpolations, right? I do 1 on the back, 1 on the front, and then I combine 3. So even it's called bilinear, I do 3 operations, but I do 1 along each axis. This is why it's called bilinear. And you can also do this in 3D, then it's called trilinear, because we do this along 3 axes, but it means 7 computations. 3 on one side, 3 on the other side, and then a 7th to combine those 2 3's. Okay, but let's focus on 2D here. So let's focus on bilinear interpolation. How do we compute that? Let's try to put this in formula. Now I'm looking at this thing from a top, right? So how do I do an interpolation along this axis here, along the x-axis, and I just call the parameter alpha. Why don't I just call it x? Because this alpha ranges from, well, from here to here, right? So these 2 points, they have x coordinates that they don't necessarily have to be 0 and 1, right? This might be 4 and this might be 7. So I first have to take this x here in between and normalize it to 0 and 1, which basically means subtract the starting point and divide it by the length between these two, which is what you see here at the bottom, right? So my alpha is simply my x point of the point in question. I subtract the starting point from that one and divide it by the distance. So this way I get an alpha from 0 to 1, where 0 is all the way to the left, 1 is all the way to the right. And I can do the same with the y coordinate, okay? And then this thing I call beta. This is really just a normalization. Now using this alpha and beta, how can I do this thing here at the front? Okay, how do I do this at the front? So I take Fij, which is this function value here, times 1 minus alpha plus Fi plus 1j times alpha. Okay, so this is just linear interpolation. We've had this before. And we can observe it. This is here. 1 minus alpha times this one plus alpha times this one. Let's do a quick sanity check. Say alpha is 0, meaning we sit here. Okay, if we sit here, I want to get this point out, which means 1 minus 0, which happens to be 1, times this one, plus 0 times this one, which means this one. Okay, works. Let's do another sanity check all the way to the right, which means alpha is 1. This means 1 minus 1 is 0. This goes away. Plus 1 times this one works. Let's do the final sanity check. We're in the center. Then we expect to get the average between the two. Alpha then happens to be 0.5. It's somewhere around my neck here. 0.5. Which means 1 minus 0.5 happens to be 0.5 plus 0.5 times the 1. Well, voila, we get the exact average. And then in between, you get a smooth transition. Okay, so this here is the interpolation along the bottom. And then I say I want to repeat the process at the top. And this is this term there. So it's now 1 minus alpha, and again alpha, but using this and that f, term f. And this gives me, so this gives me this, the height here and the height there. Okay, this is this term here and this term here. Now all I have to do is combine these two terms again by this alpha 1 minus alpha trick, but now with a different alpha, namely the one that goes this way, and that happens to be called beta. Okay, so I take this here, which is the top thing, times beta, and the bottom thing times 1 minus beta, and voila, I get my point. Okay, and if I want to, I can call these terms, I can give them simpler names, and then this, I can actually see that this is the same function as this one here. Here are the simple names. Okay, so this is called bilinear interpolation. Now you might ask yourself, what happens if I would have done it the other way around? What would have happened if I first would have done it this way, like computed this point here, and on the other side, and then done it, then pulled those points in the center? And the simple truth is, I would have gotten the same result. So it doesn't matter. And here I've just written this down. So this is my previous computation that we've had on the previous slide. And I can basically just multiply this out. I'll basically just multiply the first yellow term with 1 minus beta and the second one with beta. I get this one here. Then resort things a little bit. I resort them by the alphas and 1 minus alpha. Factor alphas out and get this here, and this equals that one, and this here, as you can see, first does the beta interpolation and the alpha. So bottom line is there, it doesn't matter. So you can choose it any way you want. Okay, so this just in short, which is good. So we can just go ahead and do it any way you want. I mentioned at the beginning, this thing is not linear. And one way to demonstrate that it's non-linear is, let's just look at a certain value. Let's say this is a height field, okay? And I want to know what's the shape of a certain isoline. What's an isoline? Isoline is a line of equal height. So if you walk along a mountain ridge, you can actually find a path where you neither go up and down, right? You might end up in a one-way street or so, not one-way street, so a dead-end street. But still, you can usually walk until you stand at the very top. You can walk around your mountain at the same height, okay? And this is an isoline. So, and if you do a linear interpolation, all of your isolines are always straight. Okay, if you do this in a triangle and you interpolate the triangle, a line that has equal height is always straight, right? Why? Because, well, the triangle is always flat. Now, let's see what happens to these lines when we do this inside an object that is interpolated this way. What are these isolines? What do these lines of equal height look like? Are they straight? If they would be straight, if they would always be straight, we would have a linear function. This is, however, not the case here. And here's just a simple summary. More details on that in my stream on scientific visualization, because there it plays a bigger role. But here, just a simple, quick kind of derivation of that. So what do I need to do to figure out what's the shape of an isoline? Well, I simply set this interpolant to a constant, right? This might be constant height or constant color. Just set it to some constant c. And then I solve this, say, for x, and I look for the function that I get out. So if I do this, well, I just say c equals this stuff here, and I've called alpha and beta simply x and y here because they're along x and y axis. Okay. Now if I solve this for y, so I basically want to know what's f of x. For figuring out what is f of x, I just solve this here for y, and this is what I get out. Okay, let's just make this derivation here very short. So you now see that's f of x, right? All of the only variable here on the right side is an x. Everything else are constant. So c's are a constant height that we're interested in. The f's are the height of the 4 corner points. And what do we see? Well, we get a quotient here. And it means, well, if you have a function that's something over something else, and you can't, and the something over something doesn't happen to be a constant, what you get is a hyperbolic function, right? 1 over x is an example for that. So long story short, the isolines are not straight, they are hyperbolas. So they are curves, hyperbolic curves. So what that means is it's nonlinear. Well, you could have figured that out by just looking at the function yourself. You would have seen that it's not a linear function right away, but simply because it's x times y. But you can also look at the shape of the lines. You also see that they're not straight. What this means is for the surface is curved. So if you interpolate positions for those 4 points, the way I described, it's not going to be flat. It's a curved. It's just like a bent piece of cloth that you get as a result. What does this mean for rendering? Well, it does have some effects for rendering as well. So for instance, you can't easily triangulate it because triangles are always flat. So it has a lot of implications. But before I get to those, let's just look at a more geometric interpretation of this bilinear interpolation. Wow, a lot of nasty words here. And this is my bilinear interpolation function again. And this is, again, the idea, right? Interpolate along one side, interpolate on the other side, combine the two. But I can also read this differently, right? If I just multiply this out a little bit different, then I can say, well, okay, what do I get here? Well, if I just multiply this out and refactor it by sorting out the f's, then I see, okay, well, this f gets multiplied by a times b. And what does that mean? Well, what is alpha times beta? Not a times b, alpha times. What is alpha times beta? Well, it happens to be the area of that thing here. Okay, and then if we look more closely, what is the area? If we talk about alpha and beta here, what is the area of the total thing then? Well, this is normalized to 0, 1, right? This is alpha 0, this is alpha 1. So this happens to be normalized to 1. So I divide this by a virtual 1. Okay, so what I do is area of this thing by area of the total thing. Area of the total thing just happens to be 1, so this is why I don't see this. What happens to, say, this here, Fij plus 1? Let's look for Fij plus 1. Where is it? Fij plus 1 is here. Okay, it gets multiplied by 1 minus alpha times beta, which happens to be this here. So does this look familiar? Multiplying a corner point of a polygon by the area of its opposing kind of object divided by the total object. Okay. This looks awfully familiar. This is exactly the same idea, or it looks like, we need to be very careful here, it looks like exactly the same idea as barycentric interpolation, except that we now do it with quadrilaterals instead of triangles. The curious thing about this is that this is not the same. I mean, it's kind of the same basic concept, but it leads to a completely different function. Right? Just by going from triangles to quadrilaterals, we end up with using a nonlinear function here, suddenly getting a curved surface. But the idea is kind of the same. So this is, in a sense, it's not called this way, but you could pretend it's barycentric interpolation inside a quadrilateral. Okay, just be aware that it has a completely different result, namely a nonlinear interpolation function. And there's other nasty things to this as well. So one thing, just to give you one idea where this plays a crucial role, and that is if I take this object and rotate it, okay, and then repeat the same process axis line. Notice how I here interpolate along axis and here along an axis. If I start to rotate that, I could keep the axes, x and y. And I could try to do the same process. The consequence, I get a different result. So I have to rotate my interpolation axes along with the object. For triangles, that's not the case. For triangles, since they are linear, I can cut through any direction and I still get a linear behavior. So I can interpolate through any direction. So that means that this, one of the consequences, for instance, is that this isn't rotationally invariant, this interpolation. Okay, but and this is just one of the consequences of that one. You just need to be aware. Slight change, same idea, slight change, big result. Okay. what do we get still when we do this interpolation? Well, we turn something like this here into something like that here, okay? So we fill gaps in between, okay, and we can move from, say, wireframe renderings, and admittedly I added color texture, but just to kind of give you this basic idea, from wireframe renderings we can get to a filled situation. Now I said I added textures here, and I mentioned textures a couple of times. What's a texture anyhow? What is that idea? Okay, and let's start with a simple scene. Let's start with this very simple scene. Okay, and let's say I wanna represent this within my idea of representing colors per vertex. If that's what I do, I would need a lot of small vertices, right? So for each of these, I don't know, smileys here, I would need a ton of vertices. I can't just use a big triangle or two big triangles to represent the back side, right? I've drawn in one blue triangle here that's supposed to show you how I want to triangulate that. However, if I look at the interior of this triangle here, if I look at the color of the interior, I said an interpolation inside a triangle is linear, right? I mean, that was kind of my crucial point here. If I look at the color distribution inside the triangle, it's certainly not linear, right? I mean, it oscillates. It goes black, yellow, black, yellow, black, yellow, and sometimes even, like, depending on which direction I look, right? If I look this way here, I get yellow, black, yellow, black, black. This is not linear. This is an oscillation, right? This is a much more complicated function, right? And if I do this cleverly, I get black, yellow, red, black, and so on and so forth. So it even oscillates in multiple dimensions. So long story short, this is certainly not a linear behavior inside the triangle, and that means I can't do it. I have to do a lot of triangles that are all linear inside. So I have to do a small triangle here that just covers the yellow area. I mean, a constant area is certainly linear. The black one and the blue one. So I literally need a few thousand triangles to represent this flat object. So, and that's a problem that you're often facing. You have something that is geometrically simple. So it has a linear behavior when it comes to its geometry, but its texture, its color appearance, okay, is nonlinear. Okay, and that gave computer graphics quite a hard time for a while. So in the 60s, 70s, when computer graphics started to take off, folks would use a lot of geometry to actually get this done. And then suddenly someone came up with this idea, okay, can we just do something different? Okay, can we just be a little bit smarter here? And you might say the naive idea is very simple. Well, just stick an image or a decal to the surface. Okay, so and that might be your notion of what a texture is. I want to make absolutely clear that this is a super bad simplification of what a texture really is. So this is why I even added a fancy animation here so that no one ever forgets this. And I'll just get out of the way, and I just want to do it again. Because I'm so proud of my fancy animation. No, I just want you to be absolutely, everyone, there's one thing you take home from the texture lesson, and it's this one here, okay? A texture is not an image that you stick to a surface. Please, don't do it this way. Think about a texture as, it's usually a texture map that's a discretely sampled multi-dimensional function containing material properties like color. Okay, now you might say, this guy is nuts, right? I mean, sticking a decal to a surface is such a nice idea. Like, what the hell is that supposed to mean? I probably don't even get it right, okay? Well, it's very important still that you get it right. So, that you kind of memorize this idea. So what's this idea? This idea is, remember when I said everything's linear inside a triangle, right? If we interpolate linearly. So, what a texture does, it takes this linear function and it applies another function on top of that linear function. And it could be a sine, right? Sine, cosine. That's what I mean, right? Like, or just let's call it cosine, because sine is kind of like, it's ambiguous. Okay, so your function could be a cosine, right? So what a texture does is it applies a different function. Okay, and that's potentially multidimensional, 2D, 3D, okay? But let's keep things simple. Let's just say 1D. Along one line in your triangle, you have a linear behavior. On top of that linear behavior, you apply a secondary function that you can choose any way you want. So for instance, cosine, tangent, whatever, right? And that is a texture. That's what I want you to understand as a texture. that function can be multidimensional. Again, if you're dealing with a triangle, it's two-dimensional. It's got x and y coordinates, or we call them often u and v then. And so your function takes two parameters. So for instance, it could be cosine x or cosine u times sine v. Okay, would be a perfect texture. And often it's discretely sampled. So meaning you store your texture as a lookup table instead of your functional description. However, I should probably put this in parentheses, a discretely sampled. So sometimes the texture happens to be a texture function, and then it is really sine times cosine or whatever. Okay, but in most cases it's a discretely sampled, so it's a lookup table in 2D and 3D in 1. Okay, now you could say, well, sure, isn't that the same as sticking a decal onto a surface? I mean, and I have to admit, sometimes yes, but the sometimes is really the hard part here. Okay, so if this is my texture, this happens to be a discretely sampled multidimensional function, or in other words, a picture, right? It's just a thing that for x and y stores the color. That's a discretely sampled multidimensional function. Okay, in 2D we can literally call this picture. Okay, so in that case it sounds more complicated than it is, right? And I apply this discretely sampled multidimensional two-dimensional function here to my x and y coordinates. So I say for x and y 0, 0, pick that one. For a slightly bigger x and still y equals 0, pick that one, and so on and so forth. For 1, 1, pick that one. So you see that in this case, in this situation, this notion of sticking a picture to a surface and using this multi-dimensional discretely sampled function happens to be the same. Okay? So why did I make all this fuss with the whole fire and don't do it this way? Well, here's the answer. What if your texture is one-dimensional? One-dimensional is still multi-dimensional. What if it's three-dimensional? How do you stick a three-dimensional lookup table, okay, which is nothing but a three-dimensional grid? How do you stick that to a surface? Have fun with that notion. Or how do you do the one-dimensional texture? And these things happen, okay? You can even have 4 or 5-dimensional textures if you want to, but 1D, 2D, and 3D textures are kind of the usual stuff. Okay, so your notion of the decal, I mean, the 3D texture is really a brick. It's a cube. How do you squeeze a cube onto a surface? No way. So this is where the simple intuition breaks. Okay, and this is why I want you to learn it right. And this is what I'll explain next week. Okay, so we got again a little bit of a cliffhanger here. So in the next stream, I want to tell you how do you deal with these textures in a real system. How do you deal with any dimensional decals, if you want to stick with the sticker notion here? How do you plug them onto a surface, and how do you texture it right and get a notion, get an understanding, get an intuition so that it works with any dimension and not just a 2D thing. Okay, so with that, that's it for today for this stream, unless you have any questions. So do we have questions about what I said so far? Questions for a change. Okay, that's not a question, but still, thank you. Okay, we got a remark. Okay, yeah, so that's what I tend to say. That's what I tend to also explain in my series on how to give a presentation. So you need to be very careful with these things, but if you do, they actually work. Yeah. Did you have a preferred engine? You mean like whether I have a preferred game engine? Or what do you mean with engine? I mean, my car runs on electricity, so it's got 2 engines. I prefer those, but I'm pretty sure you don't mean that. You mean game engine, I suppose, right? So I just assume the answer is yes, in the sake of speeding things up. Do I have a preferred game engine? Not really. It again depends. So we do use, in our group, we use Unity a lot, which I think Unity is mainly used in the academic sector. The reason is it's pretty easy to use because it's based on C#, which is a pretty modern language, which is relatively easy to use. And you know C# better than I do, probably. So it's a pretty popular engine. I don't think it's very popular in the industry, in the broad industry. It's used for some projects, and some deviations or derivations of that are used in the industry. But there's other engines that are more popular because they're more performant, such as the Unreal Engine. Still popular. I'm not sure what happened to the ID engine. Yeah, so there's different engines that have different foci, so they focus on different things, and they focus on different properties. And curiously, many of these engines have been open source recently. The CryEngine is another popular engine, right? I think Amazon bought the rights for that. They call it what's Amazon's version of that one called? I always forget what they call it. But anyways, long story short, all the engines have their pros and cons, and they all need to be updated recently. I did a stream on high-level APIs, meaning those engines. They're usually scene graphs, and I made a stream on scene graphs being Lumberjack, by the way, is the name of the Lumberyard. Yeah, Lumberyard. All right, is the name of Amazon's engine. These engines outdate themselves pretty quickly, so they need to be reworked every couple of years to stay on top of things. The answer is I don't prefer one. I guess that's the simple answer. Okay. Well, you potentially know them, but not anyone else. So I try to explain that. So the only engine, I mean, you know me from late night coding. I tend to do everything myself. So the most probable answer is I don't use any engines at all. I just code it from scratch, which is probably the true answer or the honest answer. I just write the engine myself. But for general teaching projects, we use Unity. Yes, as for the next question, does bilinear interpolation stay order independent when generalized to higher dimensions? The answer is yes. If you do it in 3D, then it's called trilinear. It is still order independent, yeah, with the same argument as before. So yeah, answer is for the engine, no engine. Anything else? Okay. Well, that finally doesn't seem to be the case. Then that's it for today. That's it for this stream. Again, I'll continue with textures, with more details on textures in the next stream on computer graphics, which will be available here on Twitch and then later on the YouTube. And we'll have more on artificial intelligence or machine learning tonight in late night coding, and there'll be basics of programming lecture in German later this week. With that, that's it for today. Bye bye and stay healthy. See you next time.